entitled High Resolution SPM on Low Dimensional Materials. First of all, thank you very much for attending to this mini-colloquium, especially when taking into account the special circumstances that we are living in these days. So my name is Antonio Javier Martínez Galera from the Departamento de Física de Materiales de la Universidad Autónoma de Madrid. And today I am here with my colleague Bruno de la Torre Cerdeño from the SEC Academy of Science. So we are also assisted for our local host, who is Agustina Asenjo Barahona from the Spanish Research Council. So thank you very much, Agustina, for your assistance.
Thank you.
This mini-colloquium is focused to show the latest advances achieved on low-dimensional materials by using scanning probe microscopies. It consists of two sessions. There is one session now in the morning, which consists of two invited talks, which will be given by Professor Pavel Jelinek and Professor Jorge Cerdán. And also we have 5 contributed talks. In the afternoon session, we will have pre-recorded talks and posters. So now I would like to summarize some guidelines for the audience. So all of questions have been performed by using the chat tool. Then to make a question, you just write in the chat box during the talk. And then at the end of the talk, one of the mini-colloquium organizers will read your question to the speaker. At the end of the session, I also will ask to all of you to switch on your cameras just to have a picture. And this is more or less the introduction, and let's wait a little bit until 9:30 just to start with the first invited speaker. So ¿cómo puedo? Ahora no soy capaz de dejar de compartir la pantalla.
Ahora, when the speaker tries to share, your screen will disappear.
Okay, shall I try now?
Yes, please.
No,
sorry, optimizar. Okay, then I want to introduce to the first invited speaker, who is Pavel Jelinek. He made his PhD in physical and engineering in the Czech Republic. Then he made a postdoc in the group of Professor Fernando Flores in the Departamento de Física Teórica de la Materia Condensada de la Universidad Autónoma de Madrid. And now he is head of the Nanosurf group in the Department of Thin Films and Nanostructures of the Physics Institute in the Czech Academy of Science. He is specialized in the experimental and theoretical research of the physical and chemical properties of molecular nanostructures on surfaces. And he is going to give a talk entitled Advanced Scanning Probe Microscopy of Low-Dimensional Molecular Systems Revealing Exotic Quantum States. And then, Pavel, you can start when you want.
Okay, so thank you very much, everyone. I'll especially thanks the organizers to invite me here. I mean, of course, it's a little bit strange. It's my first talk through the internet, so I hope it will go smoothly. And also, thanks all of you for coming and for this effort to put these things together in these difficult times. So as was said, I mean, I'm going to talk about some advances in scanning probe microscopy and what we can learn from scanning probe microscopy in case of low-dimensional system. Especially, I will focus on let's say molecular chains and some which feature some exotic quantum states. So this is okay. Let me check. Sorry, I need to find. Okay. Good. So this is the first part, is the introduction. Then I will the topology, p-conjugation, and some bond length alternation. And finally, I will also mention some recent stuff we have done related to the nuclear quantum effects and especially conserved proton tunneling in one-dimensional chains. So with that, I will start some introduction. Oops, it's not working. Sorry, I have some problem. Okay, so why one-dimensional system? If we are talking about the one-dimensional system, I mean, these days everyone is focusing mostly on 2D, and one of the discoveries of 2D is that actually the correlation in 2D system is much stronger than in 3D. But now if we apply this for 1D, it's even more bizarre. Say that this electron-electron correlation is very strong. And the results of this is that actually in 1D systems, we can find very strange behavior of the matter, like Tomanagawa-Tinger liquid, Pyros transition charge, and spin density waves, high TC. And all these things basically gives rise to very complex phase diagrams. So that's also a good playground to test different theories and really look at the things in extreme scale, where basically the correlation plays a lot of role and is driven not only by dimensionality, but also by the confinement at all. And of course, we have these days pure realization of 1D system is kind of difficult. I mean, we have a material which actually show these very exotic properties of high TC, like these bulk materials with 1D order. Also, we can artificially design the quantum wires and the carbon nanotubes or conductive polymers, which I will be focusing first. But for example, when we talk about these conductive polymers, one of the let's say properties is combination of two things. The first is what we call the Pyros transition. So this is the theorem which tells us that in 1D, if we have half-filling band or half-filling band in principal metallic system, this system is unstable and it undergoes some transformation or dimerization. So it means that the distances are no longer equal. And this is very well known in chemistry, where actually we see that these linear chains, for example, if you will take the cumulene, which would be metallic, actually undergoes due to the Pyros transition, the transition, and it goes to the ethylene. So then we have what we call the bond length alternation. And this bond length alternation somehow opens the gap. So if the alternation of the bonds, like simple, double, etc., is larger, then also the band gap which we are opening in the system is much larger. So idea here is we would like to look at these systems, and actually one of the, let's say, very famous models to start to deal with this bond length alternation is so-called SSH model, which was actually in the origin of discovery of this conductive polymers. So there was an open question why this polyacetylene can be conductive, and this is actually a very simple molecule. It's linear chain where you alternate the bond of simple and double. And I think it's also very instructive to understand what the topology means in this one-dimensional system. So if you look in this polyacetylene, we can find out that actually we have two possibilities how to arrange this system. So this system, due to the Pyros, undergoes this dimerization. So we have alternation of single and double bond. But of course, we can draw it in two different ways. So this system is peculiar in the way that actually has a double degeneracy. So it means depending on alternation of the actually in the finite system, we can have different, let's say, phases of it, as is shown on this picture. And also the beauty of this, it's very simple. So you write the Hamiltonian by pen on the paper, and you can derive all the properties. So basically, this is the Hamiltonian. So we assume here that these on-site energies of each atom of carbon are the same. Only what matters are these hoppings of the neighbors interaction T1 and T2. So this is the matrix which describe, let's say, continuous system of this polyacetylene. And this could be diagonalized. And of course, if we are talking about infinite system, then we have to deal with this block theorem, which appears as this function of k, the k points here. And now the interesting stuff is that we can change, or we can vary the hoppings T1 and T2, which represent actually the simple and double bond. So if I will go one phase here to other one. It's just the continuation of the continuing changes of the ratio T1 and T2. So basically, I'm alternating the simple bond to the double bond. So doing that, I can also plot the band structure, which is very simple. And from the first point of view, what you will find out, okay, if I have T1 is bigger than T2, I will get this kind of band, which has a band gap. And then if I go, let's say, if I start to change gradually the T1 around to T2, there is a special point where actually you will find that in case of T1 equal to T2, that you will get the metallic state. And again, then if I continue increasing T2, again, I open the band gap. So from the point of view of the band structure, actually, these two limit cases, which are marked in red and green box, they are indistinguishable and in the bulk, because they will represent the same band structure. However, when we do this analysis of the Hamiltonian now, and we look at two extremes, so we rewrite again this Pauli matrix in this original Hamiltonian in Pauli matrices, we will find that actually the Z component is 0, and we have two components, Hx and Hy, and we can now start to analyze how this Hk in the space or in the diagram of Hi and Hx is behaving, and find out actually that's slightly different. So for example, this is what is in topological winding number, means when I put in the origin myself and I start to look at basically some curve. So in this case, in this particular case of red, what I will find that so now when I position as an observer in the origin, when I start to look at this curve, I will never make turn around myself. But that's changed basically when I'm in other positions. So now you see that these two guys, which has been perfectly exactly the same in the band structure, they behave slightly different in this winding number space. So this is a little bit abstract, but now what the consequence has this one when we will consider the finite chains. And that's for this reason, we go to the extreme case where one of the hoppings will be 0, another one will be 1. So now when I plot this kind of like dimerized limit, I will find out that actually here in the of this red one, I have array dimers, but in the case of this green one, what I will find out that actually there are two end states left which do not have a connection, and this gives rise to what we call now the zero energy edge state. Okay, so this is very simple and naive explanation what it means in a topology of these polymers, like this change of this p conjugation, if you want. And of course, I mean, the topology these days plays a very important role in condensed matter physics. There are many examples which where basically first, when we look at the standard band structure, we do not care too much about the phase, but now we realize that actually in certain systems, actually the phase plays an important role and it enters to what we call this topology or if you want, this Berry phase. And so far, I mean, there has been a lot of observation in 3D and 2D material, but recently also the people realized that they can observe this 1D system and the zero edge state in graphene nanoribbon. There have been two papers like 2 years ago showing that actually this system can be prepared in these p-conjugated systems. Okay, so interesting things about why we should care about the effect of topology is that actually when we approach to the phase transition between, let's say, one phase to other, by definition we are closing the band gap. Okay. And so it means, and then we have another manifestation of the change of the topology is appearance of the zero energy states at the end. Okay, so now the idea is, okay, when we are talking about the conductive polymers, so far this has been used basically to achieve polymer. We have to use the heterodoping. It means introducing atoms, heteroatoms, which have different valence, and then we actually dope the system. But now maybe we can use the concept of this quantum phase transition or topological phase transition to tune the band gap to very small numbers and then design the polymers which are made only of carbon, which features very low band gap or could be quasi-metallics. Okay, so now going back to the first slide, I mean, I was mentioned basically these 1D systems, and I think there is one problem with all these one system. If we want to understand the basics of the physics on let's say, on details, we really want to have some tool which actually, or method which actually allows us to study the properties on single polymer. And actually, if we are talking about the conductive polymers, this is typical picture of TEM, image transmission electron microscope image, when we deal with these conductive polymers. And you see this scale is of 100 nanometers, and then you see some, let's say, collections of wires, and it's always very difficult to talk about just one single wire, which would be awesome to measure, because then we can disentangle all these collective effects and impurities, etc., etc. So to overcome this, we proposed to attack the problem from combining like 3 emerging, let's say, progress in these days. So first one is called the on-surface chemistry, which allows us to synthesize on purpose the polymers on surfaces under UHV, and then this of course has a huge advantage that then later on we can use another advantage of, or another progress in field of scanning probe microscopy, which is this high resolution imaging, where actually with functionalized these days we can fulfill the dream of chemists to see, for example, benzene rings in real space. And combination of these two techniques really, I think, now opens the new way to look at the chemistry. Especially, it's not only that we have a great analytical tool which shows the benzene structure or chemical structure in direct way, but it also, the combination of this UHV and on-surface chemistry or on-surface mechanism allow us to prepare the systems which are not manageable in solutions. So for example, what I will show you in a minute, like polymers of 100 nanometers, the problem which you will find in solution is that basically they are not soluble, so you are not able to work with them anymore. And finally, I will not touch this, but it's also important, once we grow this system, we still have basically this fantastic tool of scanning probe microscopy. We can contact these chains, we can draw them, we can just pull them away, and we can measure the transport. So that's another unique property, which actually preparing these polymers, we can later on measure the transport or mechanical response of single polymer. So we can really go to the level of just single polymer, which I think is really advancing, or could advance our understanding what's going on this limit. Okay, so first, as I promised, I will go to, I'm going to talk about these p conjugation polymers and relation to topology, etc., etc. Okay, so this is one example, and I need to mention that basically this work has been done in strong collaboration, or very close collaboration, with people from India, especially David Esicha and Manatari Marti, who provide, let's say, these fantastic precursors. And so idea here is that we want to grow, or we want to study polymers when we combine acenes. So this is this part, with some groups, some bridging groups, which is consist of ethylene. And now the question is, what is the form? What is the resonance form which we will get? So one possibility is actually from chemical picture, that something like this. So it means that now you have two radicals at the end. So it means that now we have in this bridging unit, we have like what we call the cumuli, so 2, 3 triple bonds, double bonds in row, or instead we have this kind of arrangement where you have simple triple bond. And of course, this has fundamental importance then for the electronic structure of the resonance, p resonance, which we will have. Okay, now if I talk about these p-conjugated polymers, it's very complicated or delicate system, because now we have an electronic degree of freedom, but on the other hand, we have also, let's say, the phonon degree of freedom, or vibronic. So at the end, we have to combine both things. We have to combine, let's say, the phonons, and we have to combine the electrons. They live together. They are not separated. So it means if I look into this cartoon, now, of course, not all the bonds will be the same. So some of them, they will get shrink and they will get open. And this is because of this, what we call this Pyros transition, or in general, it could be considered as a Jahn-Teller distortions. So it means that always the system undergoes some relaxations, and we will have the alternation of single and double bonds. and with different possibilities of resonances. So what I want to say, you can see the system that actually you have this kind of system of springs, and apparently the springs, they are not always the same. So we have these double bonds, simple bonds, triple bonds, and not all the guys are exactly the same. And of course, then the definition of electronic structure and this phonon or relaxation of these springs will give rise to different kind of p resonances, as one which would be the closed shell aromatic, or the one which is like radical, the quinoid. And now it's a question: what is the more favorable, or what is more advantageous for the system to adopt which of the structure? And again, it's known from the chemistry. If you go from one of these guys, to tune the system from, actually again you go from this crossing level. So before you have these two guys in one configuration, then if you transform it in the second one, this is related to this orbit. In LUMO becomes HOMO, and what was LUMO becomes HOMO. Okay, and so again, it reminds somehow this transformation of the topology. When we go from one topological state to another one, we have to close the band gap. So we can call about some conical intersection or avoid crossing levels. Now, so this is what I want to show you in a minute. Is basically now when we are able to tune different number or different acenes in these polymers. Typically, if I will just consider the monomers, so if I start with benzene, anthracene, pentacene, you should see in the band gap as a function of increasing units, what I will basically see is a monotonous decrease of the band gap. But I will never close it, even though, I mean, if I go to the larger acenes, there is an open question what will happen, but still there is this monotonous decrease of the band gap. However, what I will show you in a minute is actually if I connect these acenes and I go to the polymer, I will undergo this topological transition. So I will go from the topologically trivial, or let's say aromatic phase, and I will go to this quinoid phase, which I will call it topologically non-trivial. Okay, so let's look at it. That's just a proposal. So now we can do first, before start with some heavy experiments, we can do the calculations. So either time binding calculation, which is we can also do the ZAC phase, which tells you in which topological state is it. So this is time binding calculation for the periodic system, and now you see I plot here the wave function or the of each polymer as a function of number of rings. So means for polymer, so this guy, I see that the band gap is pretty large, but now when I start to increase number of benzene units here in the acene, you start to see that the band gap is closing, and pentacene, for example, we choose the hoppings at certain value, we get exactly the metallic phase, and then we start to open again the band gap. Okay, if you look in the DFT calculations, where of course we start to in type binding, we get this metallic state because how to realize the structure. However, when we do DFT, actually you see that the trend is very similar. So we have the acenes, the monomers, there is a continuous decrease of the band gap. Now for the polymer, I do the same calculation, DFT, and with hybrid B3 lip. I start actually between 4 and 5 in decrease of band gap, and then again start to open the band gap. Okay, so it means that I have some transition here between what would call this anthracene and again, this is the band structure calculated from DFT. And now I can have a look also, it's not so difficult. And when I have an optimized structure, I can have a look and look at the distances. And again, what I see, if I analyze this anthracene and pentacene, I see that now there is a strong relativistic organization of the bond length. So here you see that this triple bond, which is shorter distance, now gets enlarged. But more interestingly, I can see actually also in this part of us, I see relatively large changes in the distances. Now, I told you that if we go from this topologically trivial phase to topologically non-trivial phase, one of the features which should appear is presence of the edge state. So far, all the calculation has been done on finite system. So now what I will do, I will look at the electronic structure of the finite system, so made of 10 units, and I will show you here the density of state, which is calculated for this benzene polymer, anthracene polymer, and then finally pentacene. So the anthracene polymer is plotted here, and you see actually that P does show there is no states at the Fermi level. So this is the calculation without those with spin restriction. Okay, so now what I see that in the case of this anthracene, we can go to the frontiers orbitals, and they are delocalized overall. However, when I start to look at this pentacene, I see that there is something on the Fermi level, so the system seems to be metallic. And now if I look to these two states, so the one would be the first, the second unoccupied, again, state which is delocalized over the whole system, but then which are presented on the Fermi level, I will find that actually these guys are strongly localized at the edges. So far, so good. So now the question is, okay, is this reality, or can we do something? Can we make this in real world? And that's what I said. For collaboration with people from India, from David Esika and Nazario Martin, who provides the precursors of these ways. And now we can put it on the surface. So the idea here is this clever idea of the people from India is to use this double bromine system, and we use the Ullmann coupling, which actually after the annealing or deposition on the gold surface, and you will scissor this carbon bromine bond, and you will get like 4 open bonds. And the idea was, okay, let's go and we will see if this is gonna happen. And indeed, what you see is when we anneal the system at certain temperature, 500 Kelvin, then you will start to see that you will start the one system on the surface. Still, we have some residual bromines on surface, but still, then using this high resolution imaging, which actually was done by one of the chairmen of the Mini-colloquia, Bruno de la Torre. Fine, actually, you can see at the first glance that we form this anthracene polymers, which are ethylene bridge. So, and again, the triple bond is very well seen in the image by this bright spot. Okay, so this is great. We have also very good agreement between calculated band structure, conduction, valence band, which also give us the confidence that basically the DFT calculations is good enough for these systems, and so perfect. Now we have a first system which we said that it's topologically trivial, so it means that this system should not feature any end state. So now let's have a look at the end of one of these polymers, which is perfectly terminated with single hydrogen, and it should be. And indeed, when you do this spectroscopy at the edge, you will find that there is no any state which would be presented at zero bias or low bias at the ends. We only see, let's say, in contrast which corresponds to this conduction and valence band. So now let's do the same experiment. So now we start with slightly different systems. Sorry, I omit here this precursor, but the precursor like before, instead of having, we now have a pentacene. Use the same reaction on the surface. So again, the pentacene is decorated by 4 bromines. The procedure is the same. We put it on the surface, we anneal it. The surface is the goal. We anneal it, and then we start to see at certain temperature the growth of these very extended polymers, which are now made instead of anthracene of pentacene, which is made of 5 benzene rings. Again, we can have a look in the predicted band structure. We can compare the FT calculations, the bulk calculations with, and again, the agreement is pretty good. So again, DFT is okay, and besides some size of the band gap. But more important is now that if we start to look at the end of the polymer, which is terminated perfectly by these hydrogens, now indeed we start to see that there is a localized state at the Fermi level, and that's basically only localized at the end. So a part of states which we see at the valence and conduction bands, now we have evidence of very strongly localized states at the edges. And again, I told you that now what we see is, what we claim is, okay, so we claim that now we have one system which is topologically trivial, the other one system is topologically non-trivial. But now the question is, what is the relation between, let's say, topology and p-conjugation? And indeed, from DFT calculation, I already mentioned, because we can have a look directly in the bond. We can see actually that there is a substantial change when we go from anthracene to pentacene. Again, what we can also see is that it's not only the bond line, but it's also the electronic density. I do some cut of electron density. Actually, I see that again, when I see the triple bond, I will get some more accumulation of electron density, because the system tends to localize 3 bonds virtually, unless when you go to the other state or this pentacene, you will see that actually this triple bond disappears. Okay, so now what we can do is we can use this high resolution imaging, and we can have a look. So first one is of anthracene. Here, the distance we see of triple bond, and in case of pentacene, and there is another system which also features this topologically non-trivial, which I will not talk about. This one is a Byzantine, again is topologically non-trivial, and we do not see this signature of triple bond. I mean, it's on the edge, but we can also have a look in the distances high in these filters. And what we can find out is actually what has been predicted by theory. We can find some features here which also goes in this line. So, and especially this bond, we can see that now it becomes, in case of this anthracene, is shorter, and in the case of this Byzantine or pentacene, it's get larger. So again, we have some, let's say, indication that indeed this, let's say, topological phase is connected to the p-conjugation. Okay, so it means that we can somehow talk about the concept which comes from the condensed matter, this topological phase. It can be adopted to the chemistry, to this p resonances of p-conjugation. And now I also mentioned, when we have this transition from, let's say, in the p-conjugation, from aromatic to quinoid, actually this has to be related to some crossing levels. So let's have a look now in what we have in anthracene and pentacene. So again, I show you here these DIDV maps of anthracene and pentacene. So this is the valence, this is the conduction bands of anthracene. And now if you see that now they swapped. Okay, so now of conduction bands, in case of anthracene, we have strong features at, and now if you look in this pentacene, so I now start to see that I start to be like the valence band. And indeed, in the DFT calculations, again, we see these things. And now just last reminder is about this berry phase, if you want. What is in topology means. So in topology, if I go, because if I calculate this berry phase or Zach phase, I do like the calculation phase of my wave functions along, and then you see here that actually this swap of the valence band in K point gives you rise to this different berry phase. So again, in case of on p conjugation, is this could be also related to this kind of like Hickel and Mobius aromaticity. Actually, in one case, which will be topologically trivial, you don't have rotation of the phase, but in case of Mobius, what you have to do is you have to change the phase to close the cycle. Okay. So, summarize the first part of my talk. I think that I could convince you that using phase transition or p-conjugation phase transition, we can use it, the proximity, to tune the band gap and achieve very low band gap polymers. And then I think that another important thing is that there is a direct evidence that there is a connection between what we call in condensed matter topological phase and the p-conjugation. Okay, and in the rest of my talk, I will go to discuss a little bit about the concerted proton tunneling, and it will hopefully be very short because I'm a little bit out of the time. So this It's very important, and it seems to be plays a significant role to understand what we have now in systems like these bonds. And also, there is a question: what is the role of this hydrogen tunneling in these hydrogen bonding compounds? And so with that, we start to look at the system, which is a little bit peculiar, very small molecules, which actually it's very simple molecule, kind of quinone molecule, where actually you can have two isomer molecules. Okay, and at the end, the proton transfer of this molecule is one, so it like between two resonances. Actually, more like instead of the conjugated system, you will two disconjugated 6p electron systems. So we start with this and we put it on the surface, on gold surface, and can start to see is that we which you see here. We have some residual molecules here, which actually find out later on by high resolution imaging that these are the extra hydrogenated molecules, because the stuff is a little bit tricky. But okay, important thing is that, let's say, if we do this deposition in low temperature, we will get very nice chains, strike chains, and which features also some edge states, which you see here. This more, so this is experiment in 5K. Now we can take the tip and we can manipulate these chains. Okay, so if we assume that these molecules are bonded by hydrogen, this is very surprising. So because hydrogen bonds is weak, so how we can manipulate these guys? Okay, and then there is another interesting point, is actually depending strongly the behavior of these guys, depending strongly if we do 4K or in 100K. So it means if we start to deposit in room temperature, we will get completely different kind of chains, which are counted. We call them counted, and these guys cannot be manipulated. When we start to manipulate it by the tip, we see very. And so now you can say, okay, these strike chains, maybe the point is that you have some impurities. So one of the native impurities would be gold atom, which actually is incorporated. Actually creates the organometallics, and this could explain this very stable mechanical stability. But unfortunately, this is not the case. We deposit the system at 5K, and there basically mobility of gold atom is very low. And sometimes when we deposit temperature, we can find very rarely some system which reminds actually we have a gold atoms incorporated. Another thing is why we believe it's not gold atom presented, because the system is incommensurable, and we basically, if you interaction with the substrate, would impose some commensurability. Other possibility would be that we have a direct bond, but then actually between regions, but then the problem is that the distance is too short to what we observe experimentally. And there are some other possibilities, especially which we can rule. Like some hydrogenation, which is not stick for the system. To understand this, from theoretical point of view, we perform this path integral molecular dynamics, because now if we want to deal with this tunneling effect of hydrogen, we need to treat this hydrogen with this proton quantum mechanically. And this is what is done in path integral, where actually the single proton is represented by beads, which are connected by rings, and this basically samples the wave function of your proton. So doing these simulations, actually what we find is first that we will look at the barrier to transfer of from one side to other. So this is what you will get from this classical DFT calculations, the barrier about B. And then when you start to use this path integral molecular dynamics, what we will find out is actually that now you see that the barrier subspecies is, let's say, concave. You will start to see that there is actually also strong degrees in the part. In this, let's say, before was kind of like saddle point. So now this is significant proton tunneling. So it means that now the protons start to also delocalize strongly inside of the barrier. And other important thing is what is shown here is that actually when one proton is hopping, that's happen when all hydrogen has to jump, because if just one jump, it means then you break the neutrality level of the molecule. So when the one hydrogen, another one has to jump, and all the hydrogen, they has to jump at the same time. So what we deal here, and we have strong evidence here, looking at the correlation of these, we can see that actually the moving here is kind of like a coherent motion of the protons around the
5 minutes left.
Sorry.
5 minutes left. 5 minutes left.
Yeah, sorry. So I'm done. So now basically with that, what we can show is that now when we use, instead of these DFT calculations, of the geometry of DFT calculation, this path integral molecular dynamics, we exactly, when we calculate AFM image, see perfectly straight chains. They agree with what we observe experimentally. So this is another evidence, strong evidence that basically we can, this proton tunneling plays a role. There is another issue, and this is the, let's say, last two slides, is this edge state. So now I told you when we look in these straight chains, we found very strong at the edge. Okay, so this is the IDV maps, and you see that especially at the end, we will find a peak which is localized in the band gap. It's not exactly symmetric, but it's inside. So what is behind all this? Okay, so again, unfortunately, this path integral molecular dynamics is not able to describe this coupling between, let's say, this vibronic motion and electronic motion. So what we opt here is to look at the time binding model. So we will take this our model. I told you that we suppose that this hydrogen is the only weak coupling in tie binding, but now because we have this proton tunneling, probably this coupling is enlarged. So what we do here, we use, let's say, tie binding model from the single molecule, and now we soon turn on the hoppings which represent this proton tunneling, so this H and DH bond. And now if you start these parameters, let's say like 0.3 or 1 EV, you can tune the system in the sense that you see this edge state. Okay, so but I have to remind, this is not topologically this is not topological edge state. This is edge state which comes from renormalization of this side due to this hopping here. Okay, so but there are like two consequences this end, and I would like to say, okay, the first, what we claim is that the proton tunneling enhances mechanical stability of the chains, and the second one, this is probably the first example where we show that this proton tunneling and the strong proton-electron coupling gives rise to new electronical states. So basically, these quantum nuclear effects drives this hydrogen bond to not so weak interaction. And finally, I would like to thank many people. Of course, this is the collaborative projects, and especially I would like to thank Bruno for this wonderful experimental images. Aleš Cahlík, who was also involved in the second part. Jesus Mendieta for the calculation and of pairs, and of course many people for the collaboration, which was very important for us. And thank you very much for your attention. Sorry to be a little bit late.
Okay, thank you very much, Pavel, for your nice talk. Now it's time for questions. Is there any question? Come on, don't be shy. Well, actually, I have a question. So how does the hydrogenation of the polymer ends take place?
Sorry?
How does the hydrogenation of the polymer ends take place? How is the mechanism of the hydrogenation of the ends of the polymer?
Yeah, this is interesting question. I mean, of course, when we show these guys, we can also find other terminations. So we are very careful when we are talking about, let's say, the pure system, where we perfectly manage to find a system where it's terminated just by these hydrogens. We can also find other systems which, and then depends if they can feature or not this. It's also somehow on the question. So how this happen? Probably, I mean, all the reaction, that's just, I can only have some educational guess. So it means, of course, when this reaction this happens in elevated temperature, and there are probably many gold atoms attacking the system. And in one moment, probably you see this bond, but also this carbon bonds, and then there is a residual hydrogen which passivates the system. But that's sure that we selectively, when we are talking systems, we selectively look only to those which are terminated by single hydrogen.
Okay, thank you very much. Is there any other question? So then let's thank to Pavel again. Thank you very much. And then we go with the next, with the other invited speaker, who is Jorge Cerdá. From the Instituto de Ciencias Materiales of the Spanish Research Council. So he made his PhD in the Instituto de Ciencias Materiales of the Spanish Research Council under the supervision of Pedro Andrés. Then he made a postdoc under the supervision of Professor Michel Van Hoff and Michael Salmeron. And since 20 years ago, he got a permanent position in the Instituto de Ciencias Materiales of the Spanish Research Council. So he is specialized in the simulation of SPM images. And today he is going to talk a talk entitled "Quantitative Determination of Atomic Backlink of Silicene by Atomic Microscope by Atomic Force Microscope." So then, Jorge, when you want.
Okay, thanks a lot, especially to the organizers. I think it's a really challenge to make this kind of congress online. It's a new experience for all of us, and I hope it's going fine because I enjoyed quite a lot of the previous talk. So honestly, I mean, for these times, I really appreciate this invitation, which is actually a privilege. I've chosen a topic which I think it really suits the topic of the colloquium, which is basically based with on a collaboration I did with a group of Ernst Mayr. They are in Basel University, and basically Remy Pollack is a postdoctor. He's the main responsible for most of the experimental results that we'll be showing. And I'm going to be, I mean, in this contribution, I did most of the theory. Okay, basically the main message is first time, as much as we know that we can use the AFM to directly measure the atomic backlink in a kind of complex structure, which in this case was silicene. Okay, silicene on silver, it was discovered in 2012. This is kind of a seminal paper. It's been very controversial. It has very nice and bad things, but you know, all in all, they were the first ones who were able to grow silicene on silver 111. Although they also made some mistakes in interpretation. And I'll show you here some. This is a usual comparison between graphene and silicene. Structurally, the main difference is flatness. Graphene is flat, it has no backing, and the distance between carbon atoms is quite short, it's 1.4, so everything is well sp2 hybridized. When you move to silicene, what you find is that naturally freestanding silicene, just from DFT calculations, it shows a correlation of 0.5, which is not negligible at all, it's quite large. And also the distances between the silicon atoms is quite large, it's 2.3 angstroms, so it's much larger than in graphene. So basically what we're having is a system of mixed sp2, sp3 bonding. Okay, if you look at the electronic structure, this is the well-known Dirac cone of graphene, and this is the band structure of freestanding silicene. One, I think it was the dashed lines, they are without corrugate, without backlink, without corrugation, and the solid line with corrugation. You see that in both cases, freestanding silicene does show a Dirac cone, although with a much smaller Fermi velocity. So in principle, what we see here, the corrugation is not really breaking the Dirac cone, the Diracness of the system. So this really made, at the very beginning, lots of, I mean, it was considered that it could be actually an advantage. When you have buckled systems, in principle, the spin-orbit coupling should be increased. Silicon is obviously more heavy than carbon, and again, the shock effect should be increased. And so soon some theoretical papers showed up, showing that they could obtain a quantum spin Hall phase or tunable band gaps playing with electric fields. So it was a kind of a system which could give a lot of play in physics. What is known, what has been achieved so far with silicene? Well, it's only been grown in a few surfaces, not like graphene. Apart from the silver 111, which has been very well reproduced, has been reported to be grown on these substrates. I'll talk about it reading if I have time at the very end of the talk. And as I say, there's a few hexagonal surfaces where it's been reported. However, what is free or even quasi-free standing silicene remains a challenge. I think it's too reactive, so it hasn't been achieved so far. There is kind of a breakthrough when they were able to build what they call a silicene-based transistor. It was a very, very complex process of transferring the silicon, and at the end they kind of were able to make a transistor which didn't show too special properties, but I mean it was still a breakthrough. Okay, so what we're going to be doing is trying to analyze reanalyze all the silicon phases on silver. It's quite complex. It's been a lot under debate. The literature is enormous about it, especially between the 2012 and 2016, 17. But still there were some unknowns. Okay, what we're going to basically be using is high resolution STM and non-contact AFM. The combination of both of the two. I think Pavel in the previous talk already showed very nice images. The trick here is to, once you have the phase you want to study on the surface, you leak a little bit of CO on the chamber, and you manage at the end to try to trap a CO with the tip. And this really enhances your resolution. It's very well known. But of course, you have to operate at very low temperatures. As I will try to show with this kind of tips, we can really hit into very, very fine details of the atomic structure, like local symmetries, bucklings, chiralities, defects, especially bucklings, as I said. And still to check that everything that we find with the AFM is correct, for the conclusions we can obtain. We've been doing a lot of simulations at the same time, basically DFT-based simulations. First, for total energies, this will tell us which phases are more stable on the surface. We've also done STM simulations. The STM simulations, we've taken care of the actual tip structure. We use non-equilibrium Green's function formalism and really explicitly simulate the tip with whatever we want to functionalize it with. Here would be the substrate with the silicene on top. And as I say here, yeah, and then we actually do explicitly calculate the current, so we actually can generate topographic maps very similar to what is generated in experimentally. And finally, to simulate the AFM images, we've used the particle probe model that was developed in a group of Pavel. It is very simple, very fast, extremely simple compared to what represents an STM simulation with the ab initio level. Here we use very simple Leonard-Jones potentials, but as you will see, the agreement is great. So I was really, really impressed by this program, which I simply downloaded. I think it's a great success for the simulation community. As I say, it's extremely fast, the simulations, and you will see that the correlation with the experiment is very, very nice. So we'll start with the 4x4 phase. This is the seminal work I showed you before. This is a very well characterized phase. It consists of 3x3 of silicon on top of 4x4 of silver. These are the STM and AFM images. They are a little bit reminiscent of the silicon 1-1. They have these triangles arranged in hexagons, and you can see that the similarity between the STM and the AF image is very similar. This is a structure that is very well known. It's kind of a silicene network where we have two types of atoms, ones which are sitting a bit higher than the other ones. Okay, the corrugation between the two is about 0.8. If you do the simulations for this structure, this relaxed structure, we see that we get a very nice agreement with the experiment. The triangles that we are seeing in the experiments are simply these high-lying silicon atoms. Most importantly, what they tried here experimentally is to try to measure directly the buckling. So what they were doing is this frequency shift of as a function of the distance, and what we found is that we could identify a bump as we came close on top of one atom or the other. Okay, so the main what we associated this distance between the two bumps is precisely with the buckling. As you can see here, we are obtaining a distance of 0.78, which perfectly correlates with the DFT. So this kind of a benchmark that seems that things are working, and with this technique, we're going to be able to obtain the backlinks between the different silicon atoms. Now we move to a different phase. This is a 2 square root 3 phase. It's also quite well known, although it's been a little bit of debate. It's basically a square root 7 times for silicon and 2 square root 3 for silver. It is not very well ordered. It does not have really long range order. It's kind of disrupted array pattern. If you look at the high resolution STM images, what you find is some spots where you have some patches where you can see the reconstruction very nicely, but also there are also loosely interconnected with many imperfections around. These are two means of the STM and AFM image. These are characterized by these rings of these bright hexagons, which is just six bumps arranged in a hexagon, and they are very similar again between STM and AFM. All of them show a local P3 symmetry, and actually you can take this symmetry around three bonds, which would be any of the opposite sides of the hexagon or the center of it. When one is trying to propose model for this structure, this kind of information is extremely useful. It really shrinks the number of trial models that you need to try. Because, for instance, basically you need to place the silicene and start placing the carbon atoms so that they respect this symmetry, this P3 symmetry. So the carbon atom, the silicon atom, sorry, they should get on top sides or FCC or HCP sides. I just showed you this case, which is the prevailing model. We made a relaxation for that one. It's again a good silicene sheet on top of it, on top, covering the entire surface. And now we have three types of silicon atoms. Ones that are sitting on the top side, and then these are the type of atoms which are kind of making these hexagons around the top side, and they are buckled. So we have some three silicon silicons that are standing up, and 3 others that are standing lower. Similar to what we were having in the previous phase in a 4x4. Okay, when we do the simulation for this structure, we can get a very nice agreement with both with the STM and the AFM images. As you can see, this hexagonal feature that we've seen here is associated to the bonds of the highest lying atoms, and these inner triangles that actually they can only be visualized in the AFM images, not in the STM images. They correspond to the same kind of triangles we were seeing previously in the 4x4. Okay, this is this buckled hexagon. What is interesting, I'll try to show you again. If you in this image in particular, what we see is that two hexagons have different. The triangles are arranged in different orientations, and they are not related by mirror symmetry, because the mirror symmetry here runs horizontal to the screen. So this points to actually some chiral. There is some chiral factor in these structures. Okay, so to simulate it, basically what we did was, this is the structure for the left, for this one for this hexagon on the left. Then what we did was rotate the entire silicene layer, keeping the symmetry. But now what we're doing is inverting the hexagon around this top side. Okay, so now the silicon atoms that were laying low, now they're laying high. Okay, the structure, they're not strictly equivalent, but or at least well, yeah, they are strictly equivalent. Our simulations, they show us a difference of only 6 electron volts, which is basically within our accuracy. Sorry, and yeah, as you can see here, you can see that the theory, these are the AFM images. You can see that we have this triangle pointing right, and here pointing left. So actually, this was the first time that we saw there was kind of chiral nature of this structure. We again measured the direct mapping between the atoms, and here is the summary. We got 0.5 and 1, which is different type of silicene atoms, which correlates perfectly well with the DFT structure. So it seems that this approach of measuring directly the muslin keeps on working well. Now we go to the most debated structure. It's probably the less studied, the most complex one, which is this square root 7 plan for silicon, and square root 13 for silver. Okay, this is kind of a large image. We have kind of a super periodicity, more or less. It's not perfect at all, and also kind of what I call a super chirality. You can see that there is kind of some vortices. They seem to have some kind of chiral nature, although we have not really studied in detail. So I say there's been a big debate on this structure. Many recent papers are actually referring to the structure for this system, which is not correct. Okay, so I think it was really worth to make a big effort here to try to settle down what was its nature. Okay, this is the SPM image of the region around the vortex, and these are the AFM images. This is the AFM image, which I think it really shows the features better. Basically, you can see that the structure is formed by different domains. In some domains, we see triangles pointing down. Some other domains, we see the triangles pointing up. And there is kind of a domain boundaries where you can see them like these squares like that. Here they are signaled. They make like 60 degrees between them, and they all kind of converge in a vortex with this kind of chiral, super chiral nature. Okay. So actually, the nature of these two domains is not really well understood. First thing, what we could imagine is they are a mirror of each other. I will try to analyze this. Okay, so we go to the high-res images. This is the STM. This is the AFM. Again, we see these triangles that we typically associate to the hexamers. But we have another two type of bonds. This one here. And the STM images, we only see one of them, but not the other one. It's like a hole. Both images, they really show you P3 symmetry. And again, the P3 symmetry can be taken around 3 axes, which is the center of the triangles, or the 2 bumps that we have in the unit cell, either the less brighter or the small one. Still, we can end up with lots of models, but the actual use of symmetry really reduces the number. Just a few tens of models instead of having to try hundreds of them. This is the one that we obtain as the most stable one. Now we have up to 4 types of silicon atoms against very high ones that are sitting on top sides. Now we have this hexamer structure again, back with the hexamers. This time they are around an HCP side, and we now have an extra atom which is also in an FCC side. Okay. After many calculations, this is the structure that shows the better energetics. Okay, the most stable one. When we did the simulations, we actually obtained a very good agreement again with the experiment. We can reproduce all the features, even the relative intensities for the STM and both for the AFM images. We can actually see the 2 bumps, one which is brighter than the other one. Okay, as I see, we can identify immediately all the features here. We have that the triangles are always related to hexamers. The brightest bump, this one here, is related to the highest lying silicon atom, and the dimmer bump, this one here, is related to the silicon sitting on the FCC side. Okay, but what about the other domain? What we obtained here is a system where we have the triangles pointing out. What about the structure with the triangles down? Well, again, we cannot obtain it by mirror symmetry. So we did the same trick as before. Just rotate the whole silicon layer, maintaining the silver intact. And this is a structure we get, which is, again, basically with the same stability as the previous one. And now we have, again, the silicon on top. We have these hexamers. Now they are, instead of, before they were around an HCP side, now they are around an FCC side. And now this single atom is sitting at an HCP, while before it was sitting on an FCC. So they're not exactly identical, these ones, but it really points to super chirality. Okay, now we change the orientation of them, and they cannot be superimposed. Again, the simulations are very similar as before. nothing really changes, but the triangles are really pointing down this time. Again, we can see the features as before. And now when we want to measure the corrugation, now it's not so clear, actually it's not so direct as before. We have to do some fittings to potentials. I can show you later if you want to. But it's, for the buckling, but still we got an almost perfect agreement against a DFT. It really shows that, you know, it's really working for this system perfectly, this way of retrieving the atomic bucklings. We also try to explore the line effects in some detail. So this is kind of a flow up here. It's better, I think, it's easy to look at the AFM image. You can see here a domain with triangles up, the domain with triangles down, and here they are all mostly down. These are the domain boundaries. They look like squares, but actually in the SPM images they look different. These are the boundaries, and here they say that there's an equivalence between the two diagonal. I mean, only the diagonal parts of this 4-atom structure is equivalent. While here they look like pairing in this way. Okay. So it's, actually I found quite nice this distinction between the two images, which is very subtle. Okay, to try to construct a model for this is a bit clumsy. We just basically tried to place the atoms that we knew were bright, would give us these signals on one side, also on the other, and try to fit the atoms in the middle, in the borderlines, and see what happens. Okay, this is just placing the triangles in accordance with what would be a domain up and a domain down. And this is now when we make bigger the rest of the silicon atoms, which are these blue balls would be the low-lying silicon atoms. And initially, without relaxing, this is what we get when we calculate the AF image for this structure, which is a very abrupt interface between the two of them, with no signal of these ones. Now we relax the system, and what we saw is that immediately we could retrieve this line, this defect here. Basically, the structure has, the system has restructured at the border, and we find this dark silicon balls that they have raised up to accommodate the line defect. So it was kind of quite surprising in principle to see that we have a very nicely graphene graphene sheet is on top of this silver, and it's not disrupted. Basically, you can see that we still have hexagons here holding the two domains, but the other things are distorted, but they are not. They keep on being hexagons, which is quite surprising and a little bit unexpected when looking at the images. Okay, actually, when we finish this in the process of writing, I found out this paper. There are so many papers on silicene at that time, it was impossible to read all of them. I came across this one. They interpreted these previous images of this group, and they actually hit with the best model. It was a very speculative paper, and they didn't make any calculations. They just tried to rationalize what was the finding, the experimental findings so far. And I had to admit that it totally coincided with my conclusions, and they really drew a very nice model about it. And it would have been a pleasure to have known this model before I did the calculations. Anyway, okay, I concentrate now on the glassy regions, which is they appear at boundaries between two phases. You know, the 4x4 to the square root 3. These are not a kind of distorted region, and then when you make a blow up on them, what you can see is that you see kind of a distorted silicene, highly distorted. It's very similar to what happens in many carbon. I mean, this kind of distortion you can see them in many graphene sheets, but it's hardly seen on silicon. Okay, actually, you can see an heptamer. Here you can have two pentagons, and just say the pentagons in silicene are very difficult to see. I mean, they've been reported for some very complex silicon reconstructions like this one. Or recently, work we did with a group of Autónoma, with Chema Rodriguez, where we found one-D wires, one-dimensional wires, wires of silicon, solely made of pentagons. And I'll be not talking about that. Again, we can take that and measure the direct buckling here between the glassy region and the two phases. Okay, I just show you as an example, but we can here perfectly obtain the buckling values, although we don't have any theoretical values to change to compare. If we now address the electronic structure of this system, in the seminal paper, as I said before, they claimed that they had seen a Dirac cone. This was the system without silicene. This was when they absorbed silicene, and they claimed that they were seeing this Dirac cone here, which would be slightly endowed. Immediately also another group, with STM, and based on different patterns between the first and second layer of this material, they also deduced that they could see a Dirac cone. The theory jumped into this and totally refuted that. So there appear many papers that in reality there was no Dirac cone, but there was a very strong hybridization between silicon and the first layer of silver bands, and no evidence of Dirac cones at all. Even there was some experimental evidence, but they couldn't find it. Still, recently there was a paper where they showed that, well, maybe there are no Dirac cones at the K points, but they measured, they claimed they were seeing Dirac cones at the M, along the KN direction, and actually even two of them, symmetry. Okay, we see here they raised the temperature so they could occupy the states above the Fermi level, and they could actually derive these Dirac cones. So we try to address this point here, because it had not been first addressed from the theoretical point of view. First, I'll show you the band structure we have here. It's a kind of awkward band structure. I calculated the Green's function method, so the surface is totally semi-infinite, so we have a really continuum of bands. We can do projections on different atoms. So here what I'm doing is putting on gray the projection of the substrate. On red, I'm putting on top the projection on the first silver layer, and in blue the projections on the silicon atoms. So as we see a continuum of bands. When we have these marked edges, is that we typically have band edges of the bulk band. And anyhow, you can see any of the three phases doesn't show any Dirac cone at all, as it could be expected from the previous works. Okay, we can see a strong hybridization between silver and silicon, close to the Fermi level in all the bands. The unoccupied part is more silicon type, but as I say, we can rule out any Diracness on this surface. When we want to interpret what is known about the RPES data for this phase, we compare against the work of Feng et al. As I showed here. We measured RPES along three different directions. Here are the experimental RPES data, and here is what I've decided to place it. We just show the silicon band structure of the reconstruction of the 4x4 phase in blue, and on top of it, I've superimposed the signal from the silver 110 surface and folded. Okay, so when you see, what you see here is that along this direction, the only thing experimentally is this bright brand here, and actually coincides very nicely with the band edge of the bulk silver band. So it seems that they are really looking at the silver state, which probably they have a photoemission signal much stronger than silicon. Another direction, the M gamma direction, again, the blue is the band structure folded of the 4x4, and on top of it, I put the band structure of the silver. And we can see that this feature that we're finding here is perfectly correlated with this band gap that we see here. Okay, it's the edges of this band gap. So again, we really believe that they're really looking at the silver state, at some very intense silver state, which coincide with the edges. This direction, the K prime MK, where they said that they had two Dirac cones, is the most interesting one because it's mostly a gap. It's gap. This is the only projection of bulk band states. Okay, so they were claiming that this structure here was, these two were the Dirac cones. When we look at what we get theoretically, we get a very nice agreement. This parabola is probably the edge, this intense band that we're seeing here. Maybe some part of silicon around here, this electron pocket, but the surface band that we're seeing here is by no means a Dirac cone. Okay, it's totally covalent, typical covalent bonding with a nice band maximum. So conclusions of this part then will be that I think that working with non-contact AFM is extremely interesting. It really gives you, complementary with STM, it's extremely powerful. it really helps you in trying to determine these structures. One of the main achievements experimentally is to obtain the direct backlink in Silicene within a very, very good resolution, typically for below 0.1, not always, but in most cases below 0.1 angstrom, okay, directly from the frequency shift curves. So I said, we've visited all the phases. I think we made a very nice or very neat determination of the most complex one, the big one, the square root 13, and in agreement with many previous works, well, we want to see the diagrams. If I have some more time, which I think I do, I would like briefly to mention silicon and iridium. This is in collaboration with people at Autónoma, with Antonio Valera and José María Gómez Rodríguez. Okay, what is, as I said at the beginning, it was growth of silicon and iridium was first reported by this group in 2013. Okay, no one has been able to reproduce this structure, square root 3 times square root 3 and square root 7 square root 7. A few years later, or 5 years later, there was a group that actually just refuted this structure. They said there was no way to obtain it. It was a core level study with a couple of lead and DFT calculations. And basically what they were able to obtain an older structure, but they claimed there was an alloy of silicon and iridium. Before you obtain this structure, which would be at a high coverage iridium, well, they claimed that there would be some non-well-ordered structures with basically silicon atoms sitting at 3-4 sides. This is the results of Antonio and Sema. This is a transparency courtesy from them. You can see that this is a function of coverage and temperature. At high coverage, they can retrieve perfectly well this alloy phase, square root 19 alloy phase. At intermediate coverage, it coexists either with a 2x2 phase, which looks like that, and or with a 2x2 or a 4x4, which has this kind of holes here. And even if you lower the coverage, you don't see this alloying, and you get some patches of maybe 2x2 or even 4x4 if the temperature is increased a little bit. Okay, so we've been fighting with these structures, first with the order structures for some time now. I've done this calculations with my postdoc Araceli. We've tried a lot of structures, lots of them, and so far we have no success. Okay, this is the closest we have got to the 2x2 structure, which would be also silicon bilayer forming 2x2 with just one missing atom. But I think we're still far from being convinced that this is structure. And you know, quite surprisingly, the 4x4, which seems quite simple, since there should be some silicon missing here, something like that, we're really having troubles to retrieve this kind of structure. Actually, because when you retrieve one of these silicon atoms, you have all these dangling balls that give a really bright signal on the STM image. So we don't really know the nature of these holes yet. The system is quite complicated because it's not there are really out of equilibrium phases, low coverage, islands, they don't typically cover the whole system. And I'm thinking that maybe we'll have to go into thermodynamics soon to try to understand it. Okay, so that's all for now. Thanks a lot for your attention and for the organizers as well.
So thank you very much, Jorge, for this nice talk. We have some questions in the chat, so I will read them for you. The first one is from James Lawrence. He said that maybe he's missed, but how much control do you have over the formation of these different phases?
It's all temperature. It was all how you say, it was all reported already. There were many papers, and Remy actually just followed all the protocols that were reported in the previous papers. It's typically temperature, then with temperature and coverage, I guess, the amount of silicon that you deposit. I cannot really give you the details. They're in the paper, but I mean, I didn't run the experiment. But as I said, he just followed the protocols that were published to retrieve all these phases. So he could actually set them quite easily.
Okay. Next question is from Emmanuel Martinez. And he asks, do you have any experimental evidence about the nature of the topmost layer? So he means, how do you know that is pure silicene and not a silicon silver alloy surface?
That was for there was another phase of silicon that it was claimed. I can't remember, it was in the square root 3. I think there was some intermixing. We are not sure about that phase. We didn't address that phase. But I think with all the 3 phases we've shown here, which we believe they are silicon pure, I think that the excellent agreement that we achieved, and also with the fact that they totally coincide with the optimum energies, DFT energies, I think it's a strong evidence that we're hitting the correct phases. As I said, there's another phase that we didn't even grow it, which there's been a debate on it if there's some incorporation of silver on it. But as I said, these 3 phases we really think are pure just because of the good agreement. Everything matches so well that I think this is a very strong evidence.
Okay, thank you. There is another question from Bruno de la Torre. Did you see any inhomogeneous charge distribution within the silicene layer?
As far as I saw, no. I mean, it would be great if, maybe the experimentalists, they saw many more images than I saw. They might answer that better. All the data I had, it was quite well-ordered phases because we were concentrating on that actually.
Okay, another question from Saul Garcia. Did you use vacuum conditions to avoid possible reactions with ambient conditions, or it is not relevant for these measurements?
Well, this is all high ultra vacuum, low temperature. This is kind of, really careful experiments on the groups of in this group in Basel, the group of Esmelia. They have an excellent machines for doing these highly accurate measurements. I don't know if that was the question. Or, everything is done into a high vacuum.
Yeah. So I have maybe is there? Okay. Yes. Saul said thank you. I have also another question. In the 2^√3 phase, did you calculate the electronic structures for both enantiomers just to see whether the electronic structures are similar or are different?
To be honest, I don't remember. I probably did. And I'm sure they're very similar, but probably there are small differences among them. I can't remember if sorry, I cannot answer you better than that. Even I did that, but I did that 1 year ago, and I can't remember. I did it for sure. Now I remember, I did it for sure. And then, hang on, at my age, we memory goes that. But now I remember, and yeah, they were very, very similar, extremely similar. Now I remember.
Yeah, it makes sense because the formation energies are quite similar.
Yeah, exactly. But I was a bit scared of saying that, but now I do remember it. I remember the graph I did, and they were very similar. Yeah, sorry.
Okay, Jorge, thank you very much for this nice talk.
Yeah, thanks to you for sure.
So the next talk will be given by José Ortega from the Departamento de Física Teórica de la Materia Condensada, Universidad Autónoma de Madrid. He is a specialist in the theoretical simulations of complex surfaces and interfaces. And his talk is entitled Two-dimensional sublattice melting and charge order transition in potassium tin silicon 101. So please,
okay, thank you, Antonio, for the introduction. And I also wish to thank the organizers of the conference, and in particular the organizers of this colloquium, for their work in preparing this unusual conference, and also for giving me the opportunity to present our work here in the colloquium. So the work I'm going to present is a collaboration between experimental group of Hanno Wittering in the University of Tennessee and our theoretical group in the Universidad Autónoma de Madrid. The outline of the talk is the following. We will first discuss the atomic structure for the ground state of the system. And then we will see what STM and STS can tell us about the evolution with temperature of this system. Next, we will see what insights we can get from density functional theory simulations regarding the dynamics of the potassium and tin atoms on this surface. And finally, we will put all the evidence together and try to say something about the atomic mechanisms of the melting transition in the potassium-tin atomic layer. So first, let me say why this system is interesting. Well, probably there are several reasons, but let me just point out one, which is that this system displays a novel melting transition for a real atomic system, two-dimensional. And this we can study using what is going on here in this system using STM, STS, and DFT. In particular, in this system, we have a two-dimensional melting transition in the potassium sublattice, and which is coupled to a charge order transition in the tin host lattice. So this is the host lattice. The host surface is a well-known surface with tin on silicon. This is 1/3 of a monolayer with a √3/√3 surface. This is a well-known surface where we have tin atoms on T4 positions on the silicon surface, and they have this geometry. This belongs to a family, to a group of surfaces which are similar, with tin or lead atoms on top of silicon or germanium-111. And one of the particular things that these systems display is a transition from the room temperature symmetry, √3/√3, to a 3/3 symmetry at lower temperatures for these three systems, but not for the system we are now using in this work. So we deposit in this surface 1/6 of a monolayer of potassium atoms, and these are the STM images that you can get at a small negative bias, 1.5 volts. You can see these bright atoms, which are, they form a Kagome lattice. You can see this in this inset, bigger image, which are these atoms here, these blue atoms that we call the tin up atoms. In a small positive bias, so we are seeing here empty states, we see these bright atoms forming a triangular lattice, which are these red atoms here, which are the tin down atoms. And if you go to larger positive bias, what you observe in STM is this honeycomb lattice, which corresponds to the potassium atoms. So DFT, with DFT, we confirm this structure as the lowest energy, most stable one. And we can also obtain some details. For example, the difference between the tin up and tin down heights. So the tin up atoms are 0.23 Armstrong higher than the tin down atoms. That's why we call them tin up or tin down. And also the potassium atoms are above the tin up atoms by around 0.75 Armstrongs. Well, also the calculation of the density of states and the STM simulation confirms the experimental STM images. So this Kagome lattice corresponds to the occupied dangling bonds in the tin up atoms. The triangular lattice corresponds to the empty dangling bonds in the tin down atoms, and the the honeycomb lattice corresponds to potassium atoms. Now we turn our attention to the evolution with temperature. We start with the evolution of the homolume states as observed with STS. Here we have the spectrum at different temperatures, and these tick marks here indicate the maximum for the HOMO state or for the LUMO state. And in this figure on the right, we can see the HOMO-LUMO gap as a function of temperature, and we can see, we can notice here this decrease in the HOMO-LUMO gap that goes from 0.85 eV here to 0.6 in a temperature range between 120 and 200 Kelvin. SPM topography for the voltage of 1.5 eV minus, so occupied states. At 77 Kelvin, at low temperature, we see this structure, which corresponds to the 4 out of phase 2√3 by 2√3 domains that we have in this surface, indicated by the different colors. So I have to say what these are, these 4 out of phase. I'll go back to the structure. So in the unit cell, in the 2√3 by 2√3 unit cell, there are 14 atoms, for example, these 14 atoms. And depending which one of them is the down atom, we have a different ground state, so we have a different domain. So these are the 4 different domains that we have here, which are out of phase. Now, when you increase the temperature and you get close to room temperature, we start to see in these STM images also a √3 by √3 lattice, which is shown in these gray areas here. These gray areas that you can see in the images they have a √3 by √3 lattice for the thin atoms. And then if you cool down, you produce now a single domain at low, at 77. So using these STM images, you can calculate, you can count and calculate the area fraction that is covered by the ground state, by the 2√3 by 2√3 phase for the different dopings. And well, in this figure, you can see that up to 200 Kelvin, the whole surface is completely filled by this phase. And then starting at 200, there are some regions which are the √3 by √3 areas. And finally, there is this decrease close to room temperature, a sharp decrease. And let me stress that the shift in the energy gap that we were observing before with STS is taking place in the region where we have a 100% surface in the ground state. So in this region over here. So before 200 Kelvin. Okay. So now let's see if we can get some insights of what are the atomic mechanisms for this transition using DFT molecular dynamics. So in this molecular dynamics, we have to use a small unit cell, but the idea is to get, using this cell, to get a good insight on the motion of the potassium atoms and how this motion of the potassium atoms on the surface is coupled to the thin relaxation, the thin up and down relaxation. And essentially, the main results that we get from these molecular dynamic simulations at different temperatures is that the potassium atoms start to diffuse along the surface above around 200 Kelvin, and they do it by jumping between different sides of a honeycomb lattice. In fact, these sides are the T4 sides for the silicon 111 surface, excepting those T4 sides that are already occupied by the thin atoms. So they move jumping through the sides of a honeycomb lattice. And once potassiums move on the surface, well, the distinction between thin up and thin down is lost, and all the thin atoms are equivalent in a time average. So this is the √3 by √3 phase. So still we need to understand what is going on here before 200 Kelvin, where we have this decrease of the HOMO-LUMO gap. And in order, and as I said before, this is taking place where we still have a 100% surface in the ground state. So we, in order to understand that, we have analyzed the short-range positional fluctuations of the potassium atoms, possible fluctuations of potassium atoms. For this purpose, we use a 4√3 by 4√3 unit cell, which is a big one. And here we have the density of states for the ground state, the black line. This is the gap, the HOMO-LUMO gap. And the density of a state where one potassium atom has been shifted from the original position in the ground state to this new position. So there is this jump of the potassium atom from position 1 to position 2. And this gives rise to two new states, dangling bonds, which corresponds to these tin atoms, tin 1 atom, which was originally in the ground state, it is a fully occupied dangling bond. Now it is a fully occupied dangling bond that has moved into the gap. And this other state corresponds to this other tin atom, which initially was an empty dangling bond, but now, due to the presence of the potassium atom nearby, moves also into the gap. So this is empty, so the gap is now reduced. So these fluctuations, we have also calculated the energy barriers for these jumps from 1 to 2 or 2 to 3. And the energy barrier from 1 to 2 is 0.16 electron volts. And once the atom is in position 2, the barrier for a further jump to move away is 0.20 electron volts. But the barrier to return to the original position, it is only 0.09 electron volts. So if you make the calculation at 150 Kelvin, it is much, much more likely that once the atom is here, it will return. Instead of going away, it will return to the original position. So these are indeed short-range fluctuations of this type. The atoms, the potassium atoms, jump to a nearby position, but then they return. So the long-range order is not lost. Okay, so let me briefly summarize what is the picture that emerges from all this analysis. So in red here we have the information regarding the potassium sublattice, and in blue the information regarding the tin sublattice. So below 130 Kelvin we have a two-dimensional solid, so the potassium atoms are in a periodic system, and we also have a charge order state in the tin lattice. Above 130 and between 130 and 200 Kelvin, we have short-range positional fluctuation for the potassium atoms that we have just discussed. The atoms go and come back. But these short-range fluctuations still keep long-range order in and the charge order in the tin sublattice. Above 200 Kelvin, potassium atoms start to diffuse on the surface. They move over longer distances, and this gives rise to this nucleation of √3 by √3 domains, where the potassium atoms are moving. And finally, above close to room temperature, above 275 Kelvin, we have the complete melting of the potassium sublattice and the complete collapse of the tin charge order. And I think I can put the summary. So in summary, we have analyzed a novel two-dimensional melting transition for a mixed potassium and tin monolayer on silicon 111. And we have found that the melting transition goes through two intermediate regimes. The first one, which are the short-range positional fluctuations in the potassium sublattice that preserve the long-range order, and a second intermediate regime where the potassium diffusion takes place over longer ranges and this gives rise to the nucleation of high T domains and the starting of losing the long-range order. So, thank you for your attention.
Thank you very much, Jose, for this nice talk. Then I think we have 2 questions in the chat. So the first one is from Jorge. He asks, if you increase the potassium coverage, wouldn't you block these phase transitions?
Of course, if you increase the potassium coverage, then you have a different system and the behavior will be a different one. I mean, the experimentalists have increased they control the potassium deposition and they can increase that, and then they get a new system, and the new system will have a different property.
Okay, thank you. The next question is from Bruno de la Torre. Have you seen any in the phase transition from step edges?
Sorry, can you repeat?
Have you seen any in the phase transition from step edges?
From the step edges, if I will have seen any.
Maybe, Bruno, you can explain your question.
Hi, sorry. Yeah, I missed to put the role. If you have seen any role from the step edges of the surface in the phase transition.
Okay. So far as I know, no, I don't know. So this is a question for the experimental group. So this has not come up in the discussion, so I guess it doesn't.
Okay, so I have another question. Could you go back to the slide when you show the thermal evolution as observed with SPM?
This one?
Yes. So after annealing, then you cool down back again to 77 Kelvin. Did you study in detail the phase transition in this direction?
No, no, this is a good question. No, I asked the experimentalists because, of course, this was a very interesting thing to do, and somehow they could not cool down, they could not study the phase transition in the cooling down direction. I don't know why. Probably they have to do it more quickly. I don't know what is the reason. And also, unrelated question to your question is, it will be also interesting to analyze the phase transition starting from this single domain. Yeah. And the question and the problem is that the experimentalists, they couldn't do it because the surface get contaminated, and once they get to this single domain, they don't have good resolution to study anymore the surface.
Yeah. Also, starting from that conditions, would be interesting just to study the possible role of defects in the phase transition.
Right. Yeah.
Okay, thank you very much, Jose, for this nice talk.
Thank you, Antonio.
So next talk will be given by Pablo Merino from the Instituto de Ciencias de Materiales de Madrid of the Spanish National Research Council. So the talk is entitled Mechano-optical switching of a single molecule with double emission. So, Pablo?
Hello? Do you see me?
Yes.
Somehow I have problems right now. Okay. Are you seeing my screen?
Yes.
Okay, perfect. So we go. Okay, so thank you very much for your introduction. Today I'm going to talk to you about some recent works that I've been doing in close collaboration with a group of Martin Svek in the Academy of Science of the Czech Republic. Actually, we have teamed up and we are, we are he's bringing his expertise on non-contact AFM, and I am helping him in moving into the photon STM business, which I did during my postdoc in the group of Klaus Kern. And the work that I will be presenting today was mostly performed by G.D. Doletza, which is the student who performed most of the measurements that beautiful measurement that I will be showing now. Okay, let me see. Yes, okay. So this is the outline of my talk. First, I will give a brief introduction of STM-induced luminescence. I will talk on excitons on single molecules, some remarks. Then I will show to you our combined photon STM non-contact AFM setup, which we are the first group to put these two techniques together. And later we'll go to the science part, where I will show you two different systems, zinc phthalocyanine, and I will show you the role of the tip and the substrate on the photon intensity. And then I will go to copper phthalocyanine, which I will show you that how the nanoenvironment can affect the exciton state and the photon energy. And I will finish with some conclusions on everything. So the fact that there is light coming out from a tunnel junction in an STM is known almost from the beginning of the STM field itself. But the field really had a boost in since 2010, when the group of Wilson Ho published this paper, where they were able to see submolecularly resolved photon maps of a single molecule. Okay, in this work, they were studying manganese porphyrin on top of a thin aluminum oxide layer, and they were able to, by injecting current into the molecule, generate electron hole pairs that recombine as photons. And what they saw is that actually you can get, depending on where do you inject into the molecule, you can get two different emissions. The blue one here when you inject on these two lobes, and the red one when you inject on the other opposite red lobes. Okay, and this really boosts the field, and people started to look for other systems, and rapidly, well, in 2015, the group of Cheng Chaodong in China, they discovered this system, which has become a prototypical system of STM, photon STM or STM-induced luminescence studies, which is phthalocyanines and zinc phthalocyanine, in particular, on top of salt layers on silver in this case. And in this paper, what they found is, okay, here we have another photon map, and we see the emission, which is a sharp line at particular energy. And what they found here is that these molecules are extremely sensitive to their environment. And they demonstrated this by putting molecules together. And here we have an example of they manipulated single molecules to get chains up to 4 monomers. And they saw in the photon maps, where you see the lighter is the higher intensity. And very importantly, what they saw is that the energy of the emission changed depending on the number of molecules that they were seeing. So 4 molecules do not emit like 4 molecules together. They do not emit like 4 molecules isolated. It changes the emission, and this is because you are coupling the molecular dipoles, and you are getting a new quantum emitter, supramolecular quantum emitter. And last year, okay, we got another important paper on the field from the group of Yusu Kim, and what they found is that for PTCDA, you could see electron hole pairs that decay not only from the singlet state, but also from the triplet state, okay? So the singlet state is where you have anti-parallel spins, and the triplet state is where you have parallel states. So let me go to some remarks on excitons in single molecules. And first thing I want to tell is that the exciton concept is for condensed matter system. So it's meant for standard systems where one will expect the electron hole wave function to be delocalized throughout all the crystal. And this is particularly true for inorganic semiconductors. Recently, we have seen many works on the TMDs, two-dimensional materials, where you can have these Barnier excitons. And for other crystals, which are made of molecules, molecular crystals, on the contrary, the excitons are much are closer bound together. The electron and the hole are bound together in single molecules, and then what we call a Frenkel exciton, which is again delocalized on a single molecule, but on all the molecules together. And if they are in the first neighbor molecules, then we have charge transfer excitons. So what I want to say here is that when we're talking about single molecules, the word exciton is not fully justified, but it's been a consensus in the community to call electron hole pairs in single molecules excitons. Okay, but it's the same difference as an electron in a band is not the same as an electron in a single molecule, in a molecular orbital. And today I will be talking about zinc phthalocyanine and copper phthalocyanine, and what I want to show you is that for closed shell molecules, what you have is you can have singlets and triplets, and you see here that when we promote one electron from the ground state to the first electronic state available, it can have either a spin anti-parallel, and then you have a singlet exciton, and this will be a spin allowed to decay into a single photon, or it can be parallel, and in this case it will be spin forbidden to decay, and this will take much longer to decay as a photon, actually through an intersystem crossing, and this will be a phosphorescence event. When you have an open cell molecule, this is again a simplification, that you have only one electron on the highest occupied molecule. If you promote it, then in principle that doesn't matter which is the orientation of the spin, because the two levels, the two electrons on the lower level are depopulated and both are spin allowed. So in principle, open shell molecules and doublet emitters can be much more efficient than closed shell molecules. Okay, and this has been proposed and demonstrated in the recent years by some people doing devices out of light emitting devices out of open shell molecules. So let's go to our system. What we have done is to combine a tuning fork based instrument, IFM, with optical access, and we have studied zinc phthalocyanine deposit on 3 monolayers of salt at low temperatures. And we have studied on 2 different substrates, which are gold and silver, and with different tips, in particular with metal tips with S-wave character and with CO tips with P-wave character. And it's very important that the choice of the substrate and the choice of the tip, because then you have an efficient plasmonic pico cavity, which can enhance the emission from the pico cavity out to the far field. And what we get is for zinc phthalocyanine that you have molecules can absorb in 2 different configurations, which are steady and dynamic. Okay, and the steady is fixed on a absorption configuration, while the dynamic is rotating very fast between 2 chirally equivalent absorption configurations. And for zinc phthalocyanine, the important part is that both molecules emit at the same energy. Okay, you see here that is around 1.9, and for the steady and the dynamic, we have exactly the same emission. We can do manipulations between the 2 absorption configurations, and actually we also studied where are they sitting, and in this case, both configurations have the zinc metal atom on top of a chlorine side of the salt layer below. Okay. Here I saw that with this new instrument we can get constant current, constant height current tunneling maps, AFM and luminescence maps all together, which brings a holistic view of the electro-optical of the system of the molecular emitter. Indeed, just to remark that for getting the photon maps, we need to use high voltages in order to trigger the emission, while for getting the force maps, we normally need to be very close to the Fermi level. And well, normally for photon maps in phthalocyanines, you have a dip in the center. Okay, normally photon maps resemble the current, because there is a relation between how much electrons or charge carriers you inject with how many photons do you excite. But there is normally a dip, a minima in the center, which has to do with the inefficient coupling between the transient dipole of the molecule with the picocavity plasma modes. Okay. And as I told you, we studied for gold molecules on salt on gold, molecules on salt on silver. We see that we are using different polarities. In this case, for gold, we are injecting electrons on the molecule from the tip. In this case, we're injecting holes from the tip to the molecule. And what is important is that despite that the energy of the line, the energy of the excitons, the electron hole pairs, is always constant, the intensity can vary quite a lot depending on the choice of the tip and on the substrate. And we see here in these 4 photon maps that we have very different photon maps on the same molecule, on the same system. Okay, and this is an indication of a charge injection mediated mechanism for exciton generation. And I don't want to go into details because this is still an open issue in the community, but if you are interested, we can discuss it later. So if we go to copper phthalocyanine, again on salt, on silver in this case, we have again 2 different absorption configurations, the steady and the dynamic. We see that the steady has 8 lobes and the dynamic has 16 lobes. We can manipulate between the 2 configurations very easily for going from dynamic to steady just by applying high voltages. You switch almost with high efficiencies. For getting back, it's a little harder. You need to do some lateral manipulations, but that you see here in this series of images that we can really do it with relatively high amounts of success. And in the difference between copper and zinc for the absorption configuration is that in this case, while the dynamic molecule is sitting on chlorine atoms, the steady configuration is sitting on sodium atoms. And we can see here that in this case, the purple lines are on top of the brighter regions and the green lines are on top of the darker regions of the lattice. Okay? And actually, we don't only have SPM, but we also have AFM data, which further corroborates our interpretation. In this AFM image, we did a single image at 2 different tip heights. In the lower part, we were resolving the salt layer, and on the upper part, the molecule, and one can immediately see that the steady molecules are sitting on sodium. We also did, well, actually, this was in collaboration with a group of Pavel, and he may know better than I do, but we did the simulations, and well, the agreement is quite remarkable. We also did the DFT of the system, and what we found is that, again, good agreement with our experiments, that the orientation depends on the absorption side. So for molecules on sodium, the molecule tends to be at 45 degrees. The minimum energy is found at the molecules rotated 45 degrees, which is this configuration, which is exactly what we see here. And for the molecules sitting on chlorine atoms, what we see is that they tend to go to a rotation of 9 degrees, okay, with a slightly higher energy, but still reasonable. And these are the 2 absorption configurations that rotate, that permit the rotation, and then we have the dynamic character. But the important part of this system is that in this case, the 2 molecules do emit at different wavelengths, okay? The molecules sitting on chlorine and the molecules sitting on sodium, they emit at with 30-16 millielectron different. And actually the dynamic shows a sharp line at 1.91 electron volts, while the steady is redshifted and is broader. And in this series of images, STM images and optical spectra, we see that when we do take a spectrum on molecule on this dynamic state molecule on the position number 1, we get this sharp emission. When we do the spectrum on the dynamic molecule on the left, what we get is the same line, but with a broader shoulder on the right hand side of the energies. When we rescan the image, we see that we have the molecule switched from dynamic to steady state. And when we do the optical spectrum on this molecule, we see that we only have the redshifted broadband, but we keep that we can tell that the tip didn't change because we are keeping the same spectrum on the dynamic molecule, and we can reproduce this on the dynamic molecule by stabilizing it, and again we see the broadband here. And actually, well, and we can again take AFM images and really tell you that these molecules are stabilized. And this effect is quite robust. Okay, the energy may vary by few milli-electron volts from molecule to molecule, but the change between dynamic and steady, it's very robust. And I saw here 8 different examples for 8 different molecules on 2 monolayers of salt and 3 monolayers of salt. And we did time-dependent DFT to see if to calculate the excitons. And well, it's funny, it's curious that in this case, that is an open shell molecule. The SOMO and the SUMO are not the frontier orbitals; they are below the HOMO and the LUMO. So then the lowest energy transition, the lowest energy electron hole excitation is a HOMO-LUMO, and this may explain why
Pablo, 2 minutes left.
Okay, I'm almost done. This is basically why the emission from zinc, which is a closed cell, and copper is so close. But the important part here is that we simulated the lattice by a net of ions, and we saw that there is a 22 milli-electron volt difference in the energy, in the exciton energy between the steady and the dynamic states, which is in good agreement with the experiment. And this is because we are having some charge reorganization in the interface, and actually here we see in red and blue the decrease and increase of electron density. What we see is there is a charge accumulation at the interface, and we see that between the molecule sitting on chlorine and the molecule sitting on sodium, the charge accumulation sits closer to the molecule or closer to the interface. And of course, these changes will have to lead to some changes in the electronic structure of the molecule, and we did DIDB on the same molecule with the same tip after switching. And what we found out is that in this case, we are having a change in the exciton, in the electronic gap of 100 milli-electron volts, which is much bigger than the 20 milli-electron volts that we saw on the optical spectrum. So this is indication that we're having a change in the exciton binding energy between the 2 states of the molecule. And actually, we can calculate this because we measure the change of, we can calculate the change in the exciton binding energy between the dynamic and steady states, because we measure the difference in the electronic gaps and the difference in the optical gaps. And what we found is that there is a 79 milli-electron volts difference, which tell us that the exciton of the dynamic molecule is more stable than the exciton of the steady molecule. And with this, I finish with some conclusions that, okay, for the zinc, that we combined photon STM with AFM in UHV at 4 Kelvin, that the steady and the dynamic molecules sit on chlorine, that there is a strong modulation of the intensity between CO tips and metal tips, but the energy of the exciton remains constant. On the copper, on the contrary, we see that there is a systematic energy shift caused by subtle changes in the local environment, and this is correlated to the transport gap closing, and we were able to measure the exciton binding energy difference between both states. And if you're interested, this was published in 2 publications, one the Nanoletter in 2019 and one this year, and you can go there for more details. And thank you very much for your attention.
So thank you very much, Pablo, for this nice talk. We have one question from Bruno de la Torre, and he asked, how does the charge occurs in copper-tallosianine? Is just charge reorganization within the crystal field theory, or is charge transfer?
What do you mean by charge? By charging the molecule to get the excited state?
Maybe, Bruno, you can explain your question.
So you mentioned that you have some charge for distribution within the molecule.
Yes.
So I'm just asking you if that charge redistribution just occurs on the molecule, or there is some charge transfer from the substrate to the molecule.
In this case, these calculations, if I know well, were only because of the presence of the crystal. So it was the in this case, what we are seeing is the electron and increase and decrease, the electron accumulation and depletion of the system, which is the molecule sitting on top of the salt crystal, compared to the case where you're having the molecule on, free, the gas phase molecule. What we see is that we go together. There are, indeed, there is no significant charge transfer. This is only charge redistribution within the molecule because the presence of the chlorine and anion atoms. Okay.
Field theory.
Yeah, exactly.
Okay. I also have one question. Could you go please to the slide where you show for the copper tallocyanine the manipulation of the two molecules with the STM tip? Yes, here. Thank you. So why the solder at lower energies in spectra number 4 is much less clearly observed than in spectra number 2? Is there any fundamental reason for that?
Don't think so. No. This, in the end, I will say that these ones are taken all with the same, because you need to integrate. Okay, for getting this, you get to a constant current on top of a molecule, and you integrate for 60 seconds typically, or 2 minutes to get a good signal to noise ratio. And it strongly depends on the plasmonic envelope that you have when you measure. So here, I think it's only a matter that it's not properly normalized. But again, this you can change very easily by integrating more time or less time. So maybe in this case, it's just a matter of that this spectrum was taking 120 seconds and this one only 90, something like that, because when taking this experiment, we were afraid that this molecule will stabilize during the measurement. Okay.
Okay. Thank you very much, Paulo, for this for your talk.
Thank you. Thank you.
Now we go to the next speaker, who is Shantanu Misra from the Swiss Federal Laboratories for Material Science and Technology. His talk is entitled Mechanical-Optical Switching of a Single Molecule with Doubled Emission.
So I think that was the previous talk. So my talk would be on carbon magnetism.
Oh, sorry,
Yeah,
it
no
was a
problem.
problem of copy-paste.
Yeah. Okay, so everybody hears me and sees my screen, that's right. Okay, so welcome to my talk. I am going to talk today about how to generate or induce magnetism in polyaromatic hydrocarbons, which I will henceforth refer to as nanographenes. And my outline is going to be the following. I will spend a couple of slides talking about some model Hamiltonians and counting rule theorems that will put all of us on the same page to understand magnetism. And then I will talk about two cases of general interest, which also represent two distinct ways in which one can induce magnetism. So it could be due to sublattice imbalance, and I will talk about a much rarer case where magnetism arises without any sublattice imbalance. So the model Hamiltonian that we will spend some effort towards is a very simple mean field Hubbard Hamiltonian, and that's mathematically shown on the topmost part and graphically on the bottom part. And so essentially the first term is a tight binding, or the nearest neighbor tight binding Hamiltonian, which essentially promotes delocalization of electrons with a certain hopping amplitude T that depends on the extent of overlap of wave functions between different atomic sites. And the second term is a penalty term, and it's the Coulomb repulsion, which basically goes through every site. And if it finds that one of the lattice sites is doubly occupied, necessarily with electrons of opposite spins, then it adds an extra Coulomb repulsion term. And in the context of molecules, our tight binding term is going to induce hybridization and the second term, which is the Coulomb repulsion, is going to reduce this hybridization. So essentially, magnetism then becomes a competition between these two terms. So now let's apply this to three well-known nanographenes. So the first is a phenacene, which has armchair edges. The second is an acene, which has two zigzag edges on opposite ends. And the third is triangulene, which has a complete zigzag topology on all three of its edges. And if one only applies the tight binding Hamiltonian, then you see that for the phenacene, it has a pretty large HOMO-LUMO gap. For the acene, which has zigzag edge, the HOMO-LUMO gap shrinks to about 1/3 of its value. And finally, for triangulene, you see that it becomes a zero gap system. Now, the chemical consequence of this is that a chemist would write the structure of phenacene as shown by my pointer, and it would consist of 3 aromatic sextets. For acene, would consist only of 1 aromatic sextet, which can, however, migrate throughout the molecule. And one could also potentially write it as a resonance structure between a closed shell form and an open shell form, where you have increased the amount of aromatic sextets. Finally, for triangulene, you see that there's no way one can write a classical Kekulé structure without leaving these unpaired electrons. And so we're going to refer to these as non-Kekulé nanographenes. Now, these zero energy states are very special because in principle, some form of symmetry breaking transition could always occur that can lower the energy of this state. And it turns out that if you apply some amount of Coulomb repulsion, then you're going to spin polarize the system. So what was essentially a zero gap system has now become a gap system. So Coulomb gap has opened up, but you see that the spin symmetry is broken. So you have orbitals, now singly occupied orbitals of only one type of spin, while the counterpart spins are unoccupied. So that's shown graphically in the spin polarization plot. You see that preferentially spins of only one kind occupy the edges, while the other spin is inside of the molecule. And in principle, one may not need to do these calculations each and every time. A rather simple way of predicting these results is through these 2 counting rule theorems. The first is to predict whether or not zero energy states exist. And this is a result that comes from benzenoid graph theory, that the number of zero energy states should be twice the amount of the maximum number of non-adjacent carbon atoms minus the total number of carbon atoms. And the second is, given that you have zero energy states, what could be the possible magnetic correlations between the electrons? So this is given by the Lieb's theorem, which says that the total ground state spin quantum number of your system should be half times the difference in the number of carbon atoms belonging to the 2 sublattices. And the definition of sublattice, of course, comes from the fact that the honeycomb lattice is not a Bravais lattice, but it can be considered to be a Bravais lattice provided you take a 2-point basis, and then these 2 inequivalent carbon atoms are the 2 sublattices. And now you can apply this to the following 3 nanographenes of interest. So if you apply it to benzene, which would be like a prototypical closed shell molecule, you see that it has equal number of A and B sublattices. The number of, the choice of carbon atoms that maximizes the number of non-adjacent carbon atoms is equal to the number of one of the 2 sublattices. So there's no zero energy state, and and the total spin is 0. So for triangulene, you have a sublattice imbalance. And so the number of zero energy states becomes 2, and you have an open shell triplet case where the total spin is 1. But now coming back to benzene, the existence of spin 0 does not necessarily imply that the molecule has to be closed shell. And that's exemplified by this structure called Clark's goblet, where the choice of the maximum number of non-adjacent carbon atoms is a bit non-trivial. So if you consider this half of the molecule and you take only atoms belonging to the sublattice A, there are 10 of them, and you take this half and you take only atoms belonging to the sublattice B, and there are again 10 of them, then you end up with a total non-adjacent carbon atoms as 20, and there are 38 carbon atoms in total, so you still get zero energy states. However, since you have equal number of A and B sublattice carbon atoms, the spin is 0 now, so it's an open shell singlet. So you see how by tailoring the shapes, one can really change the magnetic correlations in nanographene. And so with that, let me come to the rather simple case first, where magnetism arises as a consequence of sublattice imbalance. And we are going to talk about the family of triangulines, and the smallest 2 members are shown here. Now they're interesting because, of course, as you increase the size of these molecules, the sublattice imbalance increases, and consequently the total spin increases. So it always ends up giving you high spin graphene fragments. And so this triangulene was published in a seminal work by Leo Gross and colleagues at IBM Zurich in 2017. And we wanted to explore a larger member of this family and understand if we can see some form of spin correlations directly with the STM. So that's the way to synthesize it. We do an on-surface synthesis. That's our precursor, which is synthesized in collaboration with a group of Xinliang Feng. It's a multi-step synthesis. And then you have the final precursor, which contains these 3 methyl groups. They're expected to cyclize on the gold surface at high temperatures, and it should give you the final nanographene. And indeed, that's what happens. So here is the overview STM image. You see that the molecule is fairly reactive in the sense that the yield is only 17% or so. But if you see these 3-fold symmetric species and you take an ultra high resolution STM image with a CO tip, you see that it corresponds to triangulene. And now what one expects from the electronic structure of this molecule is that you have 3 zero energy states in the tight binding spectrum. And once you include electronic correlations, you have the opening of a Coulomb gap, and you have 3 singly occupied orbitals. So psi1, psi2, and psi3, and they're all occupied with the spin of the same kind, so spin up, and the corresponding spin down counterparts are empty. And that's the spin polarization plot. So if one has to detect magnetism in such a compound, there are 2 things to do. The first is one should be able to experimentally detect the opening up of this Coulomb gap. And second is that given the molecule should have a quartet ground state, so spin 3/2, one should be able to find a quartet doublet spin excitation, if you say. So the first part is done. So that's a di by dV spectrum, and you see that it has 2 molecular orbital peaks at around -400 and +1 volt. So that's the opening up of a gap. So that's around 1.6 eV. And what you see in the middle row are the experimental di by dV maps at the positive and negative ion resonances. And you see that they look more or less the same in terms of the symmetry. And they agree pretty well with the mean field Hubbard simulated map. So if they were to be hybridized states, there should be a difference in the symmetry of the wave function squares, but they look more or less the same. So that proves that you have the opening up of a Coulomb gap, and what we are detecting indeed is a singly occupied orbital. So you're tunneling into and from the same orbital. To prove that the ground state could indeed be the quartet and not maybe doublet, what we did was we did some GW calculations, including the effect of the underlying surface. And so these 2 graphs show you the energy spectrum of this nanographene for the open shell quartet state and the open shell doublet state. So the 0 of the energy is fixed to the energy of the highest energy singly occupied orbital. And you see that the gap matches perfectly well. For the experimental gap matches pretty well with the open shell quartet state, but it differs significantly with the doublet state. So this gives us some confidence in saying that this molecule preserves its intrinsic magnetic state on the surface. However, we do not detect any spin excitations, which would be a much more direct proof of magnetism. In order to do so, what we do is that we make their dimers, and that's my one picture on the morphology of a triangulene dimer. So it consists of a building block, which in this case is going to be a triangulene. And it will consist of some form of covalent bridge. And both the building block and covalent bridge have a lot of roles to play. So for example, for a building block, it depends on whether you connect them through the minority or majority sublattices, and this will affect the sign and magnitude of the exchange coupling. The covalent bridge, for example, can determine the sign of exchange through the parity of connecting carbon atom, whether you have odd or even number. It could be conjugated or saturated. That will again affect the magnitude, and the length itself would of course determine the overlap of the wave functions of these 2 magnetic units. And so here's one example. You see that if you have 2 triangulenes and now they're connected by a benzenoid ring, if they're connected in this para configuration, you have no global sublattice imbalance. And so it should give you an anti-ferromagnetic ground state. But if you connect them in a meta configuration, you have a global sublattice imbalance, and this gives you a ferromagnetic correlation, so a spin 2 ground state. And if we now go ahead and actually connect these 2 triangulenes together, they actually fall pretty close to a spin 1 Heisenberg dimer, in the sense that the intra-triangulene ferromagnetic coupling, which is this J ferromagnetic, is actually huge. And when we connect them together, the effective exchange coupling between these two units is going to be much, much smaller than this intra-triangulate ferromagnetic coupling. So the energy spectrum should look like this. So you should have a singlet ground state, and you should have a triplet first excited state, and then you should have a quintet second excited state. So we can probably observe the singlet to triplet transition, but the singlet to quintet transition is of course forbidden by the spin selection rules that dictate that the total change in the spin quantum number should be 0 or ±1. So that's our precursor design for the two triangulene dimers. In one case, they should be connected directly at their minority sublattice sites, and in the other case, they should be separated by a benzenoid ring. And when you anneal these precursors, they should give these products, and indeed that's what happens. So you have these two triangulene dimers now directly connected and separated via a phenyl spacer. So we detect again the singly occupied orbitals, which is our point number 1 for detecting magnetism. I don't show that here for brevity, but the most important thing is that now if we go near the Fermi level, you actually see these inelastic steps, and the energy of this inelastic step drastically changes when you increase the spatial separation from being directly connected to separated by a phenylene spacer. So what we believe is that these are actually spin excitations. In this case, it's 14 millieV, and it drops substantially to more than 85% to about 2 millieV when you separate these two, since you're having obviously less overlap of the wave functions of these two magnetic units. And so far, it seems that one obvious way to generate magnetism is, of course, that you induce sublattice imbalance. And Lieb's theorem just tells you that you should have a total spin in the structure. But it was recognized early on that you may have certain benzenoid shapes which have no sublattice imbalance, and yet they give rise to a magnetism in the sense that you cannot draw a classical Kekulé structure. So this is from a paper called The Hunt for Concealed Non-Kekulé Polyhexes. So the concealed meaning that they have no sublattice imbalance and yet they have a non-Kekulé structure. And the smallest of them can be constructed only with 11 hexagons. And what this table shows you is that if you have 11 hexagons, then you can have a total of 141,000 polyhexes, and only about 8 of them, all of which are shown here, belong to this class of concealed non-Kekulean. So one might say that they indeed might be one of the rarest kind of nanographenes around. Now, the simplest of these, which is this mirror symmetric structure, is called Clar's goblet, which was already envisaged by Clar in 1972, and he tried to synthesize it through this ketone-based precursor, and it did not work. What we tried to do is to replace this precursor with something that might be amenable to on-surface synthesis. So a 6-fold substituted benzene ring with 2 anthracene groups and 4 methyl groups. And if you replace the Clar's catalyst with a gold 111 surface, it turns out we indeed can synthesize it. So this is how things look on the surface. You have individual molecules and you have some covalently fused clusters. Now these molecules come in 2 different flavors. One is, which I'm going to call species 1. It resides exclusively on the FCC lattice sites of the gold surface. And it looks completely symmetric, while the other, which I'm going to call 1', is exclusively found at the herringbone elbows. Now, species 1, let's talk about that first, is indeed what we set out to prove, that it's Clar's goblet. And now let's look at the electronic structure once again from a theory point of view. So now you have 2 zero energy states in the tight binding spectrum. You apply a Coulomb correlation term, a gap opens up. But this time you have equal number of...
Antano, 2 minutes left.
Yeah. So now you have spin down on the left side, spin up on the right side. You do a long range spectra and you again find the SOMOs and the SUMOs. Not only that, now you go close to the Fermi energy and you find spin excitations. And these spin excitations are singlet, which is the ground state, to triplet. And if you see, the energy of these spin excitations is 23 millieV, which is actually quite close to the room temperature thermal energy. My final slide is to prove that these are indeed spin excitations. And now I'm going to talk about species 1'. Now here is a high resolution STM image. And what you see is a disproportionate accumulation of density on the end that is not bound to the herringbone elbow. And in the Laplace filtered image, you see that the apex of the central hexagon that is actually bound to the elbow has lost considerable contrast. So we hypothesize that if this is the pristine Clark's goblet, this must be something like this, where at the elbow side, it has bound to an under-coordinated gold atom. And if it does so, DFT simulations will show you that the spin on the bound side is quenched. So you're left with a spin half system with considerable displacement of the carbon atom towards the gold. So that's the species 1'. If you do spectroscopy, you see no spin excitations, but you see a huge Kondo resonance, which is proof of it being a spin half system and quenching of spin on the upper side. Now you manipulate it out of the elbow position and you recover these spin excitations. Conceptually, something similar happens if you find species where you have hydrogen that is doubly, two hydrogens attached to the apex site, thus quenching the spin on the upper side. And so that would be a pristine Clark's goblet. That's a hydrogenated Clark's goblet. Pristine one shows this spin excitation in blue. Hydrogenated one has the Kondo resonance. You come close with an STM tip, apply a voltage pulse, kick away the extra hydrogen, and you recover the spin excitations again. So that's all from my talk. I would like to thank my mentors and colleagues and collaborators at EMPA, our chemistry collaborators at TU Dresden, the group of Xin-Liang Feng, our theory collaborators for some of the work, so group of Joaquin Rossier in INL in Braga, and the group of Peter Liljeroth at Aalto University in Finland for some magnetic field experiments, and the financial support from the agencies. And thank you very much for your attention.
So thank you very much, Santanu, for this interesting talk. So there is a question from Bruno de la Torre. It is possible to shift molecules towards the elbow side?
Yes, it is. Yes, it is. If you shift the molecule towards the elbow side, you will see that if you shift them close enough, they will jump to a preferential binding site where they will just interact with the gold atom and you quench the spin.
So there is a question from David Cecija. Thank you for this brilliant talk. Have you seen in any of your nanographenes a displacement movement of the energy position of the spin excitation steps while applying a magnetic field?
That's a good question. No, we haven't. And I think the reason for that is that these steps, so let me go back to one example, let's say for the Clark's goblet, you see that these steps are extremely broad. So they cover a range of something like 5 to 10 millieV. And the Zeeman splitting that you would expect in very high magnetic field would be a couple of milli-electron volts. So no, there's no displacement.
Okay, thank you very much. There is a final question, again from Bruno de la Torre. Have you tried to dope the molecules with adsorbates?
You mean by, say, some atomic species for charge transfer? No, we haven't, but yeah, that's of course a good idea. I mean, one obvious step would be to put them actually on a magnetic surface and study them. But yeah, no, we haven't. I mean, gold seems to be the one place where we can detect everything in a pristine way. And so we are so far sticking to that.
Okay, thank you very much, Santanu, for this very, very interesting talk.
Thank you very much.
So next speaker will be James Lawrence from the Donostia International Physics Center, San Sebastian, and his talk is entitled Utilizing Alkene and Halogen-Based Coupling Strategies to Study Pyrene Linkages at Surfaces.
Okay, can you hear me properly?
Yes.
Is it okay? Okay, cool. I'm sorry, I'm having to use my phone's internet connection because my internet at home is really unstable. So apologies in advance if it goes wrong midway. Okay, so my name is James Lawrence. I'm a postdoc in the group of Dimas Garcia de Teiza in San Sebastian at DIPC. Today I'm going to show you some on-surface chemistry which we use to basically look at linkages between different pyrene moieties on a gold surface. So we're using two different kind of functional groups to make a variety of linkages between these pyrenes, and here's a nice example at the bottom. So just a quick summary of the talk. So I'll briefly go over why we're looking at pyrenes and this molecule in particular. Also the possible reactions that this precursor can undergo, which there are a few, and then also look in the on-surface chemistry that we see, as well as using high-resolution STM to study the structures. And with a quick aside about the role of bromine in the chemistry on surface, and then finally finishing up with looking at the electronic properties of the different links between the pyrenes. So the reason people are interested in pyrenes is because they're quite often used in molecular electronics, both in kind of the sort of basic form with substituents attached, as well as like in polymers with lots of different linkages and so forth. So they've been used in various applications like OLEDs, OFETs, and so forth. And naturally, the kind of links between these pyrenes can have a big effect on their electronic properties, which is why it could be interesting to look at them. So what we're actually going to do here is we're going to use on-surface chemistry to study this precursor here with the alkyne and the bromine substituents, which can both undergo various reactions on the surface and form lots of different linkages. So if we look at the basic reactions between the molecule can undergo on surfaces, there's a few like just kind of basic ones here, such as Ullmann coupling, which in this case, if you think about it on a surface, it's probably not going to happen because there's quite a bad steric clash at the sides here. But it can also undergo alkyne-alkyne homocoupling, for example, the Glaser coupling, or maybe like heterocoupling between the bromine position and the bromine position and the alkyne, forming a bond like this. As well as this, there's lots of cycloaddition kind of reactions that can occur, especially with the alkyne group. So one example of this is shown here in a kind of maybe unrealistic portrayal here, but this is an example of a 2 + 2 + 2 kind of reaction where the alkynes could bond together and form like a central phenyl ring here. So what we do is we sublime this molecule onto a gold 111 surface held at room temperature, and it self-assembles into some nice little dimers on the surface at a low coverage, which is about 0.3 monolayers. I'm not going to go into this because it's not that important to the message of the talk, but if you're interested, you can ask about it. So if we then heat this up to some quite large temperature steps of 100, 200, and 300 degrees annealing temperatures, we can see that when we go to 100 degrees, we can already start seeing that some reactions have occurred. However, there are still quite a significant amount of precursors and dehalogenated monomers and so forth. So we really need to look and focus on the 200 and 300 degree steps for the kind of fully reacted samples. So as you can see, there's lots of different species on the surface. There's various dimers, some trimers, and even some tetramers here. So obviously there's probably quite a lot of different linkages between these pyrenes, which if we use STS and DIDV spectra and mapping, we can kind of understand their electronic properties. So even if it's not a particularly selective reaction, this is still kind of good for us in a way. So if we look at the main kind of most common products on the surface, at 200 degrees, we can use this high resolution STM with CO tip to identify some of the more common products. So at the top here, there's this very straight Glaser coupled dimer where there's a single bond between these two alkyne groups here. We've also got this very fused trimer here, and then also these kind of open trimers here, as well as some derivatives of the fused trimer. So these three products are particularly important to what we'll talk about in a couple of slides. Now, if we go to 300 degrees, we see some of the same products like this fused trimer. We also see these kind of dimers here, which are no longer straight, but have this offset, indicating like either one or two double bonds between them, as well as some of the products here at lower coverages, lower incidences. So if we try and use this to figure out what the main reaction pathways might be, just in a general sort of term, we can think about maybe how this monomer can fuse to form this Glaser coupled dimer. Now after this point, there's various things it can do. But if we look at the most common products, we can see that it can form this open trimer perhaps with the addition of a single monomer, which can then fuse in this central region here with cycloaddition reaction to form this kind of 5-member ring. And then this in turn can fuse even further with some dehydrogenation to form this fused trimer that I showed on the previous slide. So while these, the Glaser coupled dimer, this open trimer, and this fused trimer are quite common, we only see a few of these, which may indicate that when it's formed from this, it very quickly reacts and forms this. Now, I very deliberately haven't shown like a reaction mechanism here because there's probably several going on at once. For example, some of these species may have radicals which immediately react and form the next species and so forth. But we do see all of these intermediates in what appear to be like a hydrogen passivated form as well. Now, of course, we also form these double bonded forms of the dimer, which can also potentially go on to form this trimer and continue this reaction as well. But mainly with this system, we only see these at higher temperatures. So if they do form this, they transition very quickly to form these trimers. Now, of course, because we have both of these groups here, we can also form loads of different other products. So at the bottom here are some Sonogashira related coupling products, which is what happens when you have this alkyne group bonding to this bromine CBr position. So you have the basic alkyne product, basic Sonogashira product here, and then you can have various forms of it increasingly fused to the pyrene ring, which will significantly affect the electronic properties. And there's some other products as well. For example, the 2+2+2 alkyne cycloaddition products that I showed previously. We see some of this as well. Now, if we instead just focus, as an aside, focus on this formation of this Glaser coupled dimer, this straight dimer here, there's some potential controversy about what you actually need to form this dimer. In particular, what is the role of this bromine here? So in the literature, there are several reports of molecules of the alkyne groups absorbed on, for example, gold or silver surfaces, heated up, and the claim is that they form this Glaser coupling with a straight linkage between the alkyne groups. However, pretty much all of these don't have any nice high-resolution bond-resolved imaging, and some of them even look slightly asymmetric. And any study that do have high-resolution imaging, with, for example, this one by our group this year, actually shows an offset indicating the formation of a double bond here, rather than the straight connection between the alkyne groups. And again, my boss's old group as well, there's this formation of this double bond rather than the straight connection between the alkynes. So obviously this brings into question what the role of the bromine is in our case, because we have both the alkyne and the bromine on the molecule. So to test this, we can just take this molecule, our kind synthetic chemists can make it without the bromine for us, give it to us, and then we'll put it on the surface and anneal and see what happens. And we did this, and here is the result. So we put the molecule onto the surface. It forms these nice trimers here, which are like a self-assembled trimers based around this alkyne-alkyne interaction, which is a bit like a halogen bond. We anneal this, we get lots of different products again, but crucially, all of the dimers we see are no longer straight. They're all offset, indicating that we have not formed the Glaser product. We've formed this offset dimers, and clearly the bromine is important to forming the Glaser coupling. So there's a couple of different potential options for what role the bromine actually plays. It can be that when you heat this on the surface, this precursor with bromine, the bromine comes off, leaves behind a radical, and you get some sort of maybe surface-mediated hydrogen migration from the end of the alkyne to the side of the molecule, leaving behind a radical on the end of the alkyne, which can then go and form this Glaser coupled structure. And important aspect of this is that if you try and do this without forming a radical here, without a bromine, I think this has been shown to be endothermic in sort of theoretical calculations of another molecule on, I think it was a silver surface. So in this case, because we have no net loss of hydrogen, it's actually exothermic. So it's just like losing a bromine, basically. And we can it's also been suggested in this paper here that having bromine just absorbed on the surface nearby can actually weaken this terminal CH bond on the alkyne. And then that may itself also help this Glaser coupling to happen. Obviously, we can't prove this with what we've shown here, but these are both possibilities. Okay, so if we now come back from this aside and now turn to the electronic properties of the different links between the pyrene moieties. Obviously we've got so many different products on the surface that we can study loads of different types of linkages. So on the next slide, I'm just going to show you, first of all, like a nice wide array of dimers that we've formed. So at the top here, we've got a monomer without bromine as just a comparison. And in the center, I'm showing all of the DIDV spectra with the highest occupied and lowest unoccupied resonances indicated with the dashed lines. And we can see how, as we change these linkages, we get a very quite large decrease in the HOMO-LUMO gap, which you might expect, especially when you start fusing these rings to the pyrenes in particular. But there are some other patterns we see as well. For example, we can see going from this Glaser-coupled dimer, where there's clearly not very much conjugation between these two, because it has a very similar band gap, energy gap to the monomer. You can see forming these double bonds increases the amount of conjugation and reduces the HOMO-LUMO gap, as well as directly forming bonds to the pyrene itself in a different position. And of course, these fused rings as well. Of course, we've got all of lots of nice DIDV images as well of all these different states. And I'll talk about a couple of these in a couple of slides' time as well. So of course, we've got the same thing for trimers as well. Here are a few trimers shown here with a DIDV spectra. Again, with a monomer shown for comparison. So again, you see a kind of similar pattern where when you start forming, for example, double bonds or new rings, in particular rings that are fused to the pyrenes themselves, we get like a dramatic reduction of the HOMO-LUMO gap. And as you can see there, you can really see if you take constant height DIDV images, well, actually this is constant current, but most of the rest are constant height. You can really see where these kind of states are localized on the molecules, in particular, how they really concentrate in these new linkages that are formed. So if we try and use some kind of hand-wavy chemistry style explanations of these trends, we can kind of rationalize why they might be happening. So for example, we can consider things like the length of the conjugation path. So as you increase the number of, for example, single double bond chains between these pyrenes, we can decrease the energy gap. And this is particularly apparent, it seems, when going between triple bonds to double bonds in between these pyrenes. Because it seems that these triple bonds don't actually seem to conjugate very well between these pyrenes, possibly because of the symmetry between them. But when we increase the number of double bonds, we get quite 0.6 eV lowering of this energy gap. And you can also try and rationalize things in terms of like conjugation path length as well, the longer path reducing the gap. This is probably not a great example because we've still got these triple bonds, but you see that when you do form this molecule, for example, in comparison to this, you get quite a significant amount of kind of concentration of these frontier states around this junction in the middle here. So this is the HOMO and the LUMO. As I said before, we can also consider the formation of fused rings. Naturally, as we increase these number of fused rings attached to the pyrenes, we really reduce the energy gap. And again, this is very apparent in the imaging, as we see, for example, in this dimer with two 5-membered rings, we see a real concentration in this connection. And finally, we can consider things like cross-conjugation as well. So as a brief explanation of what cross-conjugation is, it's basically when you have a nice conjugated chain, for example, you can strictly alternate single, double bonds between the two ends. But for some structures, for example, this, if we can do this between R1 and R2, we can go single, double, and so forth. But if we want to go between R2 and R3, there's a point where we have to have two single bonds in a row. And this is what we mean by cross-conjugation.
So it seems that we have a technical problem with James' talk. Then We will try a couple of minutes in case he is able to recover the signal. And if not, then we will proceed to the next talk.
Can you hear me now?
Oh, yes, no.
Sorry, how long ago did it lose connection?
It's like 1 minute, something like that.
Okay, well, I'll just go back to, sorry about that. It's
No
super
problem.
annoying. Okay. So I'll just go through this quickly. Okay, was I up to this slide? Okay, I'm not sure where exactly the connection went, but basically.
Yes, it was something like that.
Okay, so I've probably already explained this, but the formation of the fused rings here clearly reduces the energy gap significantly with the addition of these to the pyrene rings, pyrene moieties. And then, of course, we have the effect of cross-conjugation here, where basically we can't strictly form alternating single, double kind of bond chains between different moieties. So, for example, in these two parts here, between R2 and R3, we have to draw 2 single bonds in a row, which reduces the amount of conjugation between them. And this kind of symmetric trimer here is a very nice example of this, because if we consider this as like an R group in this diagram here, to go from this pyrene to this pyrene, we have to always go through 2 single bonds, which reduces the conjugation between them. And it acts maybe more like just having a pyrene with a benzene ring on the end.
James, just 2 minutes left. Ah, okay.
It's fine, I'm at the end. So just a quick conclusion slide. We've shown how we've got a small amount of selectivity towards some products in particular with the on-surface chemistry of this precursor. In particular, we can only really form this glazer coupled structure when we have a bromine attached to the side of the pyrene. We've shown how we can form lots of different linkages between these pyrenes with all of the different products we form, and we've tried to rationalize this in a kind of hand-wavy way with some things like conjugation length, ring formation, and so forth. So I'd just like to finish by thanking people involved. This is the STS lab that I work in, and then the synthetic people, with apologies to Dulce because I don't have a picture. And for the funding, and also you for listening and tolerating the connection. Sorry about that.
Thank you very much, James, for this nice talk. So there is one question from Bruno de la Torre. He asked, did you observe frontier orbital mixing as Pavel showed when the conjugation changes from triple to double bonds in your dimers?
No, we don't. We see what appear to be strictly triple bonds in between these. So for example, in this is an image of the glazer coupled dimer. You can see in STM imaging, so the triple bonds typically appear as this kind of dark feature, whereas in AFM they appear as a bright feature. And you can see here, for example, we have 2 dark features where these triple bonds. I think if you had this mixing, you probably have to change the conjugation of these pyrenes as well. So I'm not sure how favorable that would actually be.
Okay, next question is from Jorge Lobo. The glazer coupling appears to be really inefficient compared with the Ullmann. Do you think that adding a bromine on the triple bonded carbon would reduce the zoology of the structures that you form, since you should be reducing the temperature of reaction?
Yeah, definitely. It would probably make it much more. I mean, it's been shown that you can add bromines on the end of these alkynes to form kind of a glazer coupled dimer. And if we didn't have the bromine on the side, of course, we wouldn't have all the different possible reactions that are related to Sonnecker-Shearer coupling as well. So we reduce the amount of coupling possibilities that way as well. And it occurred at a lower temperature too. So yeah, he's right.
Okay, thank you very much, James, for this very nice talk. We have to move to the next talk.
Okay.
So it will be given by Mariano Domingo Jiménez Sánchez from the Departamento de Física de la Materia Condensada of the Universidad Autónoma de Madrid. And his talk is entitled Chemical Identification with Non-Contact AFM of Xenon on Graphene. So Mariano, please, this virtual stage is yours.
Okay, so thank you very much for the introduction. As the chairman has said, my name is Mariano Jiménez and I come from the Nano SPM group at Universidad Autónoma de Madrid. And today I would like to show you our results about chemical identification with non-contact AFM of xenon on graphene. So first of all, why do this? Well, in the last year, the employment of non-contact AFM functionalized tip has been revered as a powerful tool for the characterization of molecular systems. In particular, CO functionalized tip, which presents an enhanced intramolecular resolution, has been employed for many studies, like, for example, the visualization of complex molecular structures or the study of chemical reaction on surfaces. But how are tips typically functionalized? Well, the idea is to absorb CO molecules on the same sample in which the molecules want to be studied. And after that, an in situ functionalization, I mean, picking up the CO from the surface with the tip, are performed. But what happens when this kind of tips want to be employed to study molecules on graphene surfaces? Well, there is some drawbacks, like that these functionalizations are typically performed by means of ex situ processes, like dosing CO in the chamber until a CO molecule is placed at the tip apex, or like picking up the CO from a different substrate. And here is where xenon enters. I mean, xenon could be used to carry out in situ functionalization on graphene surfaces. And why? Well, first of all, because xenon functionalized tip can achieve intramolecular resolution. And second, because this xenon has been deposited and visualized on graphite surfaces, which suggests that it could be possible to do it also on graphene. Nevertheless, it has not been explored yet. Well, and how we employ this xenon on graphene to perform in situ functionalization? Well, the idea is to try to deposit the xenon in the submonolayers regime and see if we can obtain separated region from uncovered graphene and xenon areas where the tips could be functionalized. And how distinguish this graphene from these xenon areas? Well, the first idea is to use atomically resolved images. Nevertheless, it could be difficult to do it with AFM because of the low reactivity of those species. Is there any alternative? Well, maybe force spectroscopy could be. And how does it work, this force spectroscopy? Well, it has been reported that when we have different atomic species on a surface, if we perform atomic force spectroscopy on top of each of them, we can find differences in the maximum attractive force measure. And if these differences are large enough, I mean, if we have a large relative interaction ratio, we can distinguish each species. But the question is, how much is this difference between xenon and graphene? Is large enough to allow to distinguish graphene from xenon just by performing force spectroscopy? Well, this is one of the things that we want to study in this work. And what is the idea of the work? What we want to do? Well, we want to take xenon and put it on a graphene on platinum surface. Why we would have chosen this interface? Well, because this graphene presents a low interaction with the underlying metal and a low interaction with the molecule which are absorbed on top. And which are our goals? Well, we want to study the xenon deposition in the submonolayers regime in order to see if we have these distinguished areas. We want to determine if we can employ force spectroscopy to distinguish xenon from graphene. And finally, we want to explore the extraction of xenon from this surface. And what have we employed to do this work? Well, all the experiments have been performed under ultra-high bulking condition in this system, which has an analysis chamber which is equipped with a homemade cantilever non-contact AFM, which is operated at 5 Kelvin. All the measurements have been performed at low temperature. This AFM is operated with commercial cantilever for the nanosensor company, and the data acquisition and processing have been performed by means of the RSEF-GEFES software. Well, and what's about the sample preparation? Well, the first step has been the cleaning of the platinum single crystal by means of cycle of sputtering and annealing. After that, we have grown the graphene by means of CVD of ethylene. And after this process, we have cooled down the sample to 5 Kelvin and performed measurement with the AFM in order to check the quality. The next step was the xenon deposition. In order to do it, we have raised the sample temperature to 25 Kelvin, and we have stabilized it during the xenon deposition, which consists in the exposure of the surface to a pressure of xenon. After this, we have again cooled down the sample to 5 Kelvin in order to perform the measurements. Well, and how looks the sample after all this process? Well, this is an IFM image of the surface, which shows an overview after the process. This image has been processed in order to highlight the different boundaries, in particular, this one here. Well, what we observe here is that we have 4 different regions. And the first question that comes to mind is xenon absorbed in the submonolayers regime? And if it is, where is it? Well, a first attempt to identify xenon could be, well, maybe this is graphene, those could be 2 different flakes of graphene, and perhaps this is a xenon island. Well, in order to verify that, we have acquired atomically resolved images in this square marked region. And we have obtained this. The mark of the images, the color, indicates in which region they have been acquired. I mean, this black indicates that the image corresponds to this region. If we look at these images, we can find clear differences, like the presence of a mole pattern and a difference in the lattice periodicity, being the largest one, the xenon periodicity. Attending to these differences, we can distinguish the graphene areas from the xenon region. And what can we learn from here? Well, we can learn that we have well-ordered xenon islands of the surface which present an hexagonal structure that coexists with bare graphene region. And one more, well, we can also see that the identification of xenon from overview images can be tricky. I mean, here we were wrong. Of course, we can always employ atomically resolved images to distinguish, but there is some drawbacks, like that not all tips can achieve this kind of resolution, and that this is a time-consuming process. So the question is, can we employ force spectroscopy as an alternative method for identifying xenon in a faster and nozzle-dependent way? Well, in order to answer to that question, we have performed spectroscopy measurement on the center of each imaged region, keeping the tip apex constant. From that, for this measurement, we have acquired these frequency distant curves, where the color again indicates in which region they have been acquired. The distant axis here is arbitrary. Well, what we observe, in these curves, we observe differences in the maximum frequency measured. But what's about the force? Well, we can get the force distance plot by means of the deconvolution algorithm of Sader and Jarvis, giving rise to these curves. This total force distance curve has 2 components. A first component related with the long range van der Waals interaction, and a second component related with the short range, which give us information about the chemical species which are below the tip. And we are interested on this one. In order to isolate it, we have subtracted the van der Waals force, giving rise to these short range distance curves. And what we observe here? Well, the main we observe that there is difference in the maximum attractive force that we measure on xenon and the maximum attractive force that we measure on graphene, being the lowest one, the interaction measured on xenon. And what does it mean? Well, it means that if we have an overview image like this, and we perform force spectroscopy in each of the different regions, just by looking to the maximum attractive force, we can distinguish xenon from graphene. I mean, the lower interacting area will be the xenon region. Then we don't need atomic resolved images to distinguish xenon from graphene. Nevertheless, all these have been performed with the same tip apex. Does it work for other tips? And what is the value of this relative interaction rate? I mean, of the difference. In order to answer to that question, we have performed measurement with different tips on different regions. So we take a given tip, we acquire data on graphene and xenon regions, giving rise to a first set of data that I show you here. The blue curve has been acquired on xenon and the red on graphene. We have repeated this process with another tip apex on other region, and we have obtained a second set of data. We have repeated this process many times. Here I show you as example 4 sets of data. And what we observe here is that we have a large short range dispersion as consequence of the different tips that we have employed. So how can we treat this dispersion in order to measure the relative interaction rate, to measure the relative interaction rate? Well, we can use a survey normalization. How? Well, as example, I show you the process with the first set of data. The idea is to normalize each set of data, I mean, the data acquired with each tip, to the maximum attractive form measured on graphene, I mean, to this value. And what we obtain from this process? Well, we obtain plots like this, in which if we look at the maximum attractive point on the xenon curve, we obtain the relative interaction rate between xenon and graphene. So if we take this normalization and we apply it to all this data, what we observe is that the dispersion has been dramatically reduced, and from this plot we can evaluate the relative interaction rate, which is of 69%. And what's more, well, we can also observe that the relative interaction ratio is large enough to allow a clear distinction between xenon and graphene areas, independently of the tip. I mean, we haven't observed any case in which the form measured on xenon are close enough to the form measured on graphene to give rise to a confusion. So, brief summary. What we know until now? We know that we have xenon on the surface, xenon island, and that we can identify it by means of force spectroscopy. So the next question is, can we extract this xenon from the islands? I mean, can we generate vacancies with the tip at these vacancies which are naturally present on the islands? Well, in order to try to answer to that question, we have tried different approaches. The first one was to indentate the tip. Here I show you the region where we have performed the indentation before doing. The stripes are related with the atomic periodicity of the xenon. Before performing the indentation, we have characterized the tip by means of a four distant cube, which has been acquired at this point. Well, after this characterization, we have indented the tip. And how looks the region after the indentation? Well, we observe that we have generated a big vacancy on the xenon layer. And what has happened to the tip? Well, we again perform a force spectroscopy, a force distant cube, acquire a force distant cube on the same point. And what we observe is that the maximum interaction has been reduced. And what does it mean? Well, it could mean that we have a lower reactive species at the tip. So maybe we have a xenon atom. Nevertheless, this vacancy is big. I mean, it don't seem like a very controlled process. Maybe instead of have a xenon atom, what we have done is to rearrange the atom of the tips. So in order to try to verify that actually we have a xenon atom, we have tried another approach, which consists on a scan the xenon layer with the tip closed from the xenon layer. And what we obtain from this process? Well, we obtain images like this where we can observe the xenon atoms. And in a given line, we observe the appearance of a xenon vacancy, which indicates that the xenon has been extracted from the layer, and a change on the resolution, which indicates that the tip has changed. And how looks this change on the force distant cube? Well, again, we have characterized the tip before and after the extraction, and again, we observe a reduction on the maximum attractive force, which reinforces the idea of that we have a xenon atom on the d-apex. So, summarizing this slide, the idea is that xenon can be extracted from the island, and that after this extraction, we observe a reduction on the tip sample interaction that corresponds to a xenon terminated tip. So, as conclusion and take-home message, we have deposited xenon on graphene on the submonolayers regime, and we have observed that we have separated regions of xenon and graphene. We have performed force spectroscopy on graphene and xenon areas in order to measure the relative interaction ratio between the xenon and the graphene, and we have shown that force spectroscopy can be used to distinguish xenon from graphene without need of atomic resolution. And finally, we have explored the xenon extraction, showing that xenon can be extracted from the islands, and that after this extraction, there is a reduction on the tip sample interaction that points towards a cantilever functionalization with xenon. Well, and finally, I would like to acknowledge people who have collaborated in this work, and also to people who has helped in many ways with advices, discussion, or technical assistance. And also thank you for your attention.
So thank you very much, Mariano, for this nice talk. And then there is time for question. There is one from Bruno de la Torre. Please.
Sorry.
See?
Tira.
Yes. Please, you can start typing. No. Have you seen a change in the graphene resolution after defunctionalization with xenon?
Well, what I have tried after the functionalization with xenon is to perform images on graphene, but with the feedback close. And I haven't observed a clear difference. I think that I should have tried to do it at constant height, and maybe in this way I could see a difference. I don't know if this answers your question.
Okay, I think I also have one question. Is regarding to the success rate when extracting the xenon.
Mm-hmm.
So in principle, xenon is a noble gas, and then is quite inert, and then yes. The interaction with the tip should be quite small. So typically van der Waals. So then, what you would say that is the rate of success when trying to extract the xenon?
I can give you an exact number, but it's not a really strange process. I mean, you don't have to try 100 of times to get the xenon. 50%, more or less.
Okay, thank you very much. There is another question from Jorge Lobo. Instead of AFM, did you try to use STM to find out what is on the surface? In principle, Iván Briguega showed that depending on the current, you can visualize or not the graphene on copper 111. Could this happen on the free xenon areas so you could discard what is xenon regions from the other?
I have tried to measure this also with STM, and I haven't found any parameter at which I can image the graphene below the xenon. I don't know if this answers your question. I mean, you always see with STM you have xenon or graphene, but in this case with the cantilever that we have employed, we can measure the current. So we have to do it with force measurement.
Okay, thank you very much, Mariano. We have to close here, and thank you very much to all of the speakers for these very interesting contributions. And now I would like to say something that I'm going to say something if I am able. Yes, I would like to mention that this afternoon we have an afternoon session, and it has 3 pre-recorded talks and 2 posters. So all of you are welcome to attend to this afternoon session. Thank you very much to everybody. And now I would kindly ask